Look up at the night sky on a clear, dark evening, and you see a scattering of stars, a few familiar constellations, perhaps the hazy band of our own Milky Way. It feels immense, almost infinite. But what if I told you that everything you can see with your naked eye is just your own backyard? That beyond our local galactic neighborhood lies a true cosmic metropolis, a sprawling city of galaxies so vast and dense it defies easy comprehension. This is the Coma Cluster, a gravitational island containing not dozens, not hundreds, but thousands of galaxies, all bound together in a silent, swirling dance across 100 million light-years. And within its ancient, glittering depths, secrets wait secrets that have puzzled astronomers for generations, and that challenge the very foundations of what we think we know about the universe. What if the rules of physics themselves are written differently there? What colossal, unseen forces are truly at work in this realm of giants? Today, we are embarking on a journey to the heart of this extraordinary cluster. We will be your guides through 25 of its most profound and unexplained phenomena. We're not just talking about curious oddities, we are venturing into mysteries that represent the very frontier of cosmology. Phenomena that suggest the presence of dark matter in forms we cannot yet imagine, gravitational anomalies that bend space-time in impossible ways, and galaxies that behave as if guided by some unseen intelligence. This is a place where stars vanish without a trace, where entire galaxies are stripped of their material, and where the faint, ghostly glow of something else haunts the spaces between the light. Each mystery is a piece of a puzzle so large we are only just beginning to see its outline. So prepare to have your perception of reality stretched. We are about to dive deep into the enigmas of the Coma Cluster, a journey that will take us from the breathtaking scale of its galactic collisions down to the subatomic whispers of particles we cannot see. This is more than a tour of cosmic wonders. It is an investigation into the unknown, a detective story written across the cosmos. The clues are there, hidden in the light that has traveled for millions of years to reach our telescopes. All we have to do is learn how to listen. Let's begin. Our journey into the heart of the Coma Cluster begins with its undisputed monarch, the colossal galaxy known as NGC 4889. This is not just any galaxy. It's a supergiant elliptical, a cosmic leviathan that sits at the very center of the cluster's gravitational well. We would expect such a dominant galaxy to be the very definition of a dark matter fortress, its immense gravity anchored by an enormous, invisible halo of this mysterious substance. Yet, when astronomers began to carefully weigh NGC 4889, they were met with a result that sent shockwaves through the cosmological community. The dark matter, the very thing that should be holding this giant together, appears to be missing. The numbers just don't add up. This is our first great mystery, and it strikes at the core of our understanding of how the universe is structured. To understand why this is so baffling, we need to look at how astronomers weigh galaxies, especially ones so far away. They use two primary methods, and in a stable system, these methods should tell the same story. The first method involves studying the motions of stars within the galaxy itself. In a giant elliptical like NGC 4889, stars are swarming in a vast, chaotic cloud. By measuring their speeds and directions, a technique called velocity dispersion, scientists can calculate the total mass, both visible and dark, required to keep the galaxy from flying apart. The second, often more reliable method for distant objects is gravitational lensing. According to Einstein's theory, a massive object will warp the fabric of space-time around it, bending the light from even more distant galaxies that happen to lie behind it. By measuring this subtle distortion, we can map the total mass distribution with incredible precision. Here's the conflict. In NGC 4889, these two trusted methods are telling wildly different stories. The velocity dispersion of the stars suggests a certain mass, one that aligns with the amount of visible stars and gas we can see, with very little room left for a dominant dark matter component. But gravitational lensing studies, which probe the total gravity well of the galaxy and its immediate surroundings, often imply a much larger mass is present. So, is the dark matter truly gone, or is it just not where we expect it to be? One compelling theory is that NGC 4889 has been the victim of a cosmic robbery. Over billions of years, as it orbited and interacted within the crowded core of the Coma Cluster, the immense tidal forces generated by its thousands of neighbors may have physically stripped away its dark matter halo. Think of it as a galaxy being slowly peeled apart, its invisible, tenuous dark matter being pulled out into the general cluster environment, leaving the more tightly bound visible stars behind. This leads to a profound and unsettling possibility. What if our fundamental models for how dark matter behaves are incomplete? We typically model dark matter as cold and collisionless, meaning its particles mostly pass right through each other and don't interact with normal matter except through gravity. But if dark matter can be so easily stripped from a giant galaxy, does it imply some other, more complex interaction is at play? Perhaps dark matter particles can interact with each other in ways we haven't yet considered, making them more susceptible to being scattered and removed. The mystery of NGC 4889 forces us to confront two equally revolutionary ideas. Either the environment in the heart of a galaxy cluster is far more violent and efficient at altering galaxies than we ever conceived, or the nature of dark matter itself is more complex and strange than our current physics can describe. This isn't just a missing puzzle piece, it's a question mark placed directly over one of the cornerstone concepts of modern cosmology. If the missing dark matter of NGC 4889 presents us with a cosmic deficit, then our next mystery presents the absolute opposite, a staggering and almost unbelievable surplus. Just as we have galaxies seemingly robbed of their invisible mass, the Coma Cluster also contains galaxies that are almost nothing but invisible mass. The most stunning example of this is the ghostly entity known as Dragonfly 44. From its very discovery, this object has defied every expectation. It's classified as an ultra-diffuse galaxy, a type of galaxy so faint and wispy it's barely there at all. If you were to look at it through a powerful telescope, you would see a faint, ethereal smudge of light, a cosmic phantom containing remarkably few stars for its size. It looks fragile, as if a strong cosmic wind could blow it apart, but looks, as we so often find in astronomy, are profoundly deceptive. When astronomers first measured Dragonfly 44, they expected to find a lightweight, insignificant galaxy. What they found instead was a heavyweight champion of dark matter. This faint, ghostly smudge has a total mass comparable to our own Milky Way galaxy. Let that sink in for a moment. Our Milky Way is a magnificent spiral, a brilliant pinwheel containing hundreds of billions of stars, vast clouds of gas and dust, and a significant halo of dark matter. Dragonfly 44 has roughly the same total mass, but 99.99% of it is made up of dark matter. For every one star you can see in Dragonfly 44, there are nearly 10,000 units of mass that are completely invisible. It is a galaxy in which the visible stars are merely tiny, insignificant tracers, like a few flakes of snow swirling in an invisible hurricane. This creates a paradox that is the mirror image of the NGC 4889 problem. How can an object with the gravitational footprint of a giant be so utterly lacking in the visible stuff that normally makes up galaxies? The very existence of Dragonfly 44 in the Coma Cluster makes its survival even more puzzling. The core of a galaxy cluster is a cosmic battlefield, a dense, violent environment where galaxies regularly scream past one another at tremendous speeds. In such a crowded and gravitationally intense neighborhood, A fragile, diffuse object like this should be easily torn to shreds. The immense tidal forces from bypassing giant galaxies and the overall gravitational pull of the cluster itself should have long ago disrupted its delicate structure, scattering its few stars to the winds. The fact that it hasn't been destroyed tells us one thing with absolute certainty. It must be held together by an immense, deeply anchored gravitational glue. That glue is its colossal dark matter halo, a massive, invisible sphere that acts as a protective shield, stabilizing the galaxy against the onslaught of its environment. This leads us to the central, confounding question of its origin. How does a galaxy form that is almost entirely dark matter? One theory suggests that Dragonfly 44 might be a failed galaxy. Early in the universe, a massive clump of dark matter may have collapsed, but for some reason, the normal matter, the gas needed to form stars, never fully fell into its gravitational grasp. Perhaps the gas was heated by primordial radiation or stripped away by violent events before stars could form in significant numbers. Another, more dramatic possibility is that it was once a more normal galaxy, but as it orbited through the cluster, all of its stars and gas were violently ripped away in a series of galactic collisions, leaving behind only its resilient dark matter core, a cosmic skeleton. Each of these theories has its own complications, and neither fully explains the extreme ratio of dark to visible matter we observe. The stark contrast between NGC 4889, a giant with missing dark matter, and Dragonfly 44, a wisp with an overabundance, forces a profound realization. It shows us that the dark matter story within galaxy clusters is not a simple one-size-fits-all narrative. The cluster environment seems to be a powerful and complex sculptor, capable of rearranging the fundamental components of galaxies in ways we are only beginning to map. The existence of these two extremes residing in the same cluster tells us that our models of cosmic evolution must account for a far wider and more bizarre range of outcomes than we ever anticipated. But our investigation into the Coma Cluster's mysteries doesn't end with the strange tales of individual galaxies. We must now pull back to witness one of the most colossal and enigmatic structures known to astronomy, the Coma Cluster's giant radio halo. Imagine for a moment that you had eyes that could see not in visible light but in radio waves. The familiar pinpricks of galaxies would fade, and in their place a vast, faint, and shimmering veil of light would appear, a ghostly ocean of radio emission that fills the entire core of the cluster, stretching for millions of light years across. This is the radio halo, a diffuse and energetic structure that tells us the space between the galaxies is anything but empty. It is, in fact, alive with activity, and the source of that activity is one of the cluster's most profound puzzles. This radio glow isn't just random static, it's a specific type of emission known as synchrotron radiation. To understand what that means, picture a massive particle accelerator like the Large Hadron Collider, but on a truly cosmic scale. Synchrotron radiation is produced when electrons, whipped to nearly the speed of light, spiral wildly through magnetic fields. The process is so energetic that it makes the electrons emit light, but not the kind our eyes can see. They emit radio waves, so the very existence of this giant radio halo tells us two things for certain. First, that the space within the cluster is threaded with immense, widespread magnetic fields, and second, that it is absolutely teeming with a sea of ultra-high-energy electrons. This discovery alone was monumental, but it immediately presented scientists with a fundamental problem, a cosmic energy crisis. The issue is that these high-energy electrons are living on borrowed time. As they zip through space and emit synchrotron radiation, they are constantly losing energy, and they lose it very, very quickly. In fact, they should radiate away all of their tremendous energy over a timescale that is remarkably short compared to the age of the cluster itself. They are like a firework that burns brilliantly for a few seconds and then vanishes into darkness. If nothing were actively re-energizing them, this vast radio halo should have faded into obscurity eons ago. The fact that it is still shining so brightly today means that some immense and powerful engine, must be continuously at work, re-accelerating these particles, injecting fresh energy into them to keep the entire structure glowing. The central question, then, is what is this cosmic power source? The leading conventional theory points to the immense violence of the cluster environment itself. The Coma Cluster is not a static, peaceful place. It is a dynamic and turbulent cauldron. As thousands of galaxies swarm and merge, and as vast clouds of superheated gas collide and swirl, they generate colossal shock waves and turbulence that ripple through the intergalactic medium. Think of it as a continuous, universe-sized storm, with gravitational waves and sonic booms propagating through the cluster's core. This turbulent energy could, in principle, act as a giant particle accelerator, transferring its power to the electrons and keeping them topped up with energy. This is a compelling explanation, but when astronomers run the numbers, they find a troubling inconsistency. The level of turbulence we can observationally infer from the motions of galaxies and gas often seems insufficient to fully account for the sheer power and vast extent of the radio halo we observe. The engine, it seems, might need an extra fuel source. This discrepancy has led physicists to consider more exotic possibilities, and one of the most intriguing involves the very dark matter that permeates the cluster. We've already seen how dark matter's distribution is mysteriously complex. What if its particles are also capable of providing this missing energy? The theory of dark matter annihilation proposes that when two dark matter particles collide, they could annihilate each other, converting their mass directly into energy and producing a cascade of standard model particles, including critically high-energy electrons and positrons. If this is happening throughout the Coma Cluster's immense dark matter halo, it could provide a widespread, steady, and potent source of re-acceleration, essentially using the decay of the invisible universe to power the glow of the visible one. The radio halo, in this scenario, becomes a potential indirect signal of dark matter's fundamental properties, a tantalizing hint that we might be witnessing particle physics on a galactic scale. Yet the story may be even more complex than a simple choice between turbulence and dark matter. It's possible that both mechanisms are at work in a kind of cosmic partnership. The turbulent energy from galactic mergers could provide the initial push to the particles, while a more subtle background process like dark matter annihilation provides a steady trickle of new particles to be accelerated. Unraveling the precise contribution of each is one of the great challenges in modern astrophysics, because the answer doesn't just explain a glowing cloud of radio light. It gets to the heart of how energy flows through the universe's largest structures and what the true nature of the cosmos's dominant, invisible component really is. The anomalous radio halo is more than a beautiful enigma. It is a dynamic laboratory, testing our understanding of everything from plasma physics to the fundamental nature of matter itself. Moving from the energetic glow of the radio halo, we shift our focus to the very skeleton of the cosmos, the immense and delicate web that holds the Coma Cluster together. If you could see the universe with the right eyes, you wouldn't see isolated galaxies floating in empty space. Instead, you would witness a breathtaking cosmic architecture, a sprawling network of threads and filaments, like the veins in a leaf or the neural pathways of a vast brain. These are the filamentary structures of the Coma Cluster, colossal bridges of superheated gas and, we believe, dark matter that stretch for millions of light years, connecting galaxies in a gravitational tapestry. They are not just beautiful, they are a fundamental part of the universe's structure, and their presence in Coma presents a series of profound puzzles about how such a complex system forms and evolves. The primary way we detect these filaments is through their X-ray emissions. The gas within them is not just warm, it is searingly hot, reaching temperatures of tens of millions of degrees. At these extreme temperatures, the gas glows brightly in high-energy X-rays, allowing space-based observatories like Chandra and XMM Newton to map their intricate forms. These observations reveal a stunning reality. The space between the blazing galaxies is not a vacant void but is filled with this tenuous yet immensely hot plasma, structured into long, winding rivers and sheets. What makes these filaments so scientifically critical is that they are believed to trace the underlying distribution of dark matter. According to our best models of cosmic evolution, dark matter forms an invisible scaffold first, and the normal baryonic gas then falls into these gravitational wells, heating up as it compresses. So, by studying the hot gas filaments, we are essentially reading a map of the hidden dark matter backbone of the cluster. This is where the first major mystery emerges. Our simulations of how the universe evolves, which are incredibly sophisticated, predict that these filaments should be dynamic and short-lived. As galaxies within the cluster whiz around on their orbits, they should act like cosmic plows, their immense gravitational pulls stirring up the intergalactic medium and shredding these delicate structures over time. The violent mergers between galaxy groups, which are common in a cluster's history, should generate powerful shock waves that would tear the filamentary web apart. Yet, when we look at the Coma Cluster, we see a web that is remarkably intact and clearly defined. It's as if we're looking at a spider web that has somehow survived a hurricane unscathed. This resilience is deeply puzzling. It suggests that either the filaments are constantly being regenerated by some process we don't understand, or that they are far more robust and structurally coherent than our physics models have accounted for. Their enduring presence forces us to reconsider the true balance between creation and destruction in the intracluster environment. Adding another layer to the enigma is the surprising composition and behavior of the gas within these filaments. Based on our understanding of stellar nucleosynthesis, how elements are forged in stars, we have a good idea of the chemical makeup we expect to find in the universe. When massive stars explode as supernova, they seed their surroundings with heavy elements like iron, silicon, and oxygen. We would expect this enriched material to be fairly well mixed within the cluster after billions of years of galactic winds and mergers. However, spectroscopic analysis of the X-ray light from the Coma filaments reveals a startling and inconsistent chemical distribution. Some filaments appear to be rich in these heavy elements, while adjacent structures are surprisingly pristine, composed almost entirely of primordial hydrogen and helium. This is not a uniform mixture, it's a cosmic patchwork. This uneven distribution acts as a powerful yet cryptic fossil record. It tells us that the gas flowing into the cluster along these filaments has different histories. The metal-rich filaments likely carried gas that was previously processed through generations of stars in galactic suburbs before falling into the cluster core. The pristine filaments, on the other hand, might be a direct pipeline from the cosmic wilderness, funneling gas that has remained untouched since the dawn of time, never having been part of a star-forming galaxy. The fact that these distinct populations have not fully mixed implies that the flow of gas into the cluster is still an organized, structured process, not a chaotic free-for-all. It challenges the assumption that the intracluster medium is a well-stirred cosmic soup and suggests that the cluster's assembly history is preserved in these elemental fingerprints, if only we can learn to decode them properly. Ultimately, the filamentary structures of the Coma Cluster are more than just beautiful curiosities. They are a direct challenge to our understanding of cosmic evolution on the largest scales. Their very existence and persistence provide a stringent test for our cosmological models. If our simulations cannot reproduce the intricate, robust web we observe, then we are missing a key piece of physics, perhaps related to the nature of dark matter or the complex magnetohydrodynamics of superheated plasma. They serve as a living fossil, a relic from the time when the cluster was first assembling itself, and yet they are also a dynamic part of its present-day ecology, guiding the flow of gas that will fuel future generations of stars. In their intricate patterns, we see the ghostly imprint of the universe's largest structures, a web of mystery that connects not only galaxies, but also our present questions to the ancient history of the cosmos. Now, as we continue to explore the intricate dynamics of this cosmic metropolis, we encounter a phenomenon that gives the Coma Cluster much of its distinctive character, a profound and widespread silence. Across its vast expanse, there exists an overwhelming population of galaxies that astronomers often refer to with the somber nickname red and dead. These are almost exclusively elliptical galaxies, and their title tells a complete story. They appear red because their stellar populations are old. The massive, hot blue stars that signify vigorous youth have long since burned out, leaving behind the cooler, longer-lived red giants and dwarfs. And they are considered dead because they have completely and seemingly permanently ceased forming new stars. The great cosmic factories of gas and dust that create stellar nurseries have been shut down. This creates a central mystery. Why is star formation so efficiently and universally quenched here? What kind of environment could enact such a thorough and widespread shutdown? The answer appears to lie in the unique and often violent conditions of the dense cluster itself. To appreciate the scale of this phenomenon, it helps to compare the Coma Cluster with a more familiar environment, like our own local group of galaxies. In our neighborhood, we see a vibrant mix of galaxy types. The Andromeda Galaxy and our own Milky Way are both grand spirals, alive with bustling regions of star formation, their beautiful arms glowing with the pink light of newborn stars. There are also irregular galaxies like the Large Magellanic Cloud, which are actively churning out new suns. This diversity tells us that star formation is a natural and ongoing process in quieter parts of the universe. But when you look at the core of the Coma Cluster, this diversity vanishes. The brilliant, star-forming spirals are almost entirely absent, replaced by a uniform sea of featureless red ellipsoids. It's the difference between a thriving, bustling city center and a quiet, aging retirement community. Something about life in the crowded cluster core has systematically extinguished the spark of creation in these galaxies. Astronomers have identified several brutal mechanisms that can bring about this galactic demise, and the Coma Cluster is a perfect laboratory to observe them in action. The first and perhaps most dramatic is a process called ram pressure stripping. Imagine a galaxy like a spiral rich with cold gas falling into the cluster core for the first time. It's moving at an incredible speed, thousands of kilometers per second, through the superheated, thin plasma that fills the space between galaxies. This isn't a true vacuum, it's a substance known as the intracluster medium. As the galaxy plunges through this hot gas, it experiences a tremendous headwind, a cosmic version of sticking your hand out of a car window at high speed. The pressure from this wind is so immense that it acts like a powerful force, physically grabbing the cooler, denser gas inside the galaxy and ripping it right out. This gas is the very raw material for future stars. In a single, violent event, the galaxy can be stripped of its stellar fuel, dooming it to a slow, red death as its existing stars age and no new ones are born to replace them. We can actually see the telltale signs of this in some galaxies, with long, gaseous tails streaming out behind them like cosmic comet tails, visual evidence of their lifeblood being stolen. A second, more gradual process is known as galaxy harassment. This isn't a single catastrophic event, but a death by 1,000 cuts. In the densely packed core of the Coma Cluster, galaxies are constantly whizzing past one another, their gravitational fields interacting in a relentless dance. These repeated, fast-paced gravitational encounters can be profoundly disruptive. They can torque and warp a galaxy's structure, gradually pulling it out of its elegant spiral shape into a more chaotic, blobby elliptical form. More importantly, these gravitational tugs can stir up the galaxy's internal gas, preventing it from settling down and collapsing to form stars. It's akin to trying to light a candle in the middle of a hurricane. the environment is simply too turbulent and disruptive for the delicate process of star formation to proceed. Over billions of years, this constant gravitational jostling can effectively shake the star-forming gas right out of a galaxy or render it useless. Then there is a slower, more insidious process with the fittingly grim name of strangulation. This occurs when a galaxy's supply of fresh, external gas is cut off. Spiral galaxies don't just rely on the gas they already have. They are constantly accreting new, pristine hydrogen from the cosmic filaments we discussed earlier, a slow trickle of fuel that allows them to sustain star formation over billions of years. However, when a galaxy falls into a massive cluster, the immense gravitational pull of the cluster as a whole can seize this incoming gas, preventing it from ever reaching the galaxy. At the same time, the galaxy's own internal reservoir of gas is being steadily consumed by ongoing star formation. With the tap of new fuel turned off and the existing tank being drained, the galaxy simply runs out of gas. Star formation doesn't cease with a violent bang, but with a long, slow sigh as the last generation of stars forms and the galaxy begins its inevitable transition to the red sequence. This process is harder to observe directly, but its effect is written in the chemical fingerprints of the stars in these red and dead galaxies, which show signs of having formed from a closed box system. The true mystery, however, is not that these processes exist, but the sheer efficiency and completeness with which they have operated in the Coma Cluster. The puzzle for cosmologists is that our simulations of cluster formation often struggle to reproduce a population that is so uniformly quenched. The mechanisms of ram pressure stripping and harassment are powerful, but they should leave behind some survivors. A few resilient spiral galaxies that manage to hold onto their gas, perhaps in the cluster's outskirts or on very specific orbits. Yet in Coma's core, the red and dead population is almost total. This suggests that these galaxies may have been quenched very early in the cluster's history, perhaps even before they fell into the main cluster, in the denser group environments that later merged to form Coma. This pre-processing theory implies that the journey to becoming red and dead often begins in the suburbs, in smaller groups of galaxies where these quenching mechanisms can first take hold, before the galaxies are delivered to the final graveyard of the cluster core. The overwhelming silence of the Coma Cluster's galaxies is not just a present-day condition. It is the culmination of a long and complex evolutionary history, a mystery that challenges our models of how environments shape the lives of galaxies from their earliest beginnings. But the profound silence of the Coma Cluster's galaxy population is only half the story. If you were to observe this region with an X-ray telescope, you would be greeted by a sight of overwhelming brilliance, a stark contrast to the dim, red galaxy's invisible light. The entire core of the cluster is filled with a dazzling, diffuse glow, a testament to a sea of gas so incredibly hot it shines not in visible light, but in high-energy X-rays. This is the intracluster medium, a superheated plasma that represents the majority of the normal, baryonic matter in the entire cluster, and its very existence is the source of one of the most enduring and perplexing problems in modern astrophysics, a problem known as the cooling flow crisis. To grasp the scale of this phenomenon, consider the sheer amount of gas involved. The X-ray emitting plasma in the Coma Cluster isn't just a thin haze. It's a massive, sprawling atmosphere that weighs many trillions of times more than our own Sun. This gas is not merely warm, it is searingly hot, with temperatures soaring to between 50 and 100 million degrees Celsius. At these mind-boggling temperatures, the atoms that make up the gas are moving at tremendous speeds, and they are stripped of their electrons, existing in a state known as a plasma. When these fast-moving electrons and ions collide, they emit enormous amounts of energy in the form of X-ray photons. This is why the Coma Cluster is one of the brightest X-ray sources in the entire sky, a colossal beacon of thermal energy on a truly cosmic scale. For decades, the conventional understanding of this gas led to a straightforward and seemingly inevitable prediction. This gas is incredibly dense at the very center of the cluster, and we know from basic physics that hot, dense gas should radiate its energy away very efficiently. The X-ray glow itself is the evidence of this energy loss. As the gas radiates, it should cool down. As it cools, the pressure that supports it against the immense gravitational pull of the cluster's dark matter halo should drop. This, in turn, should cause the gas to flow inward, sinking slowly and quietly toward the cluster's center in what astronomers termed a cooling flow. This inflow of cold, dense gas was expected to be the primary fuel source for runaway star formation, creating vast rivers of new stars and rejuvenating the central galaxies. It was an elegant, self-consistent theory that made perfect sense. There was just one problem: the predicted star formation never appeared. When astronomers went looking for the evidence of this cooling flow, the resulting bursts of new stars, the reservoirs of cold molecular gas that should have condensed out of the cooling plasma, they found almost nothing. The central galaxies, like NGC 4889, were not surrounded by vibrant stellar nurseries. They were, as we've seen, predominantly red and dead. It was as if a brilliant theoretical engine had been designed, only for someone to discover that the fuel line had been cut. The gas was clearly losing energy through its intense X-ray emission, but it wasn't cooling down to form stars. Something mysterious was acting as a universal heating system, continuously pumping energy back into the gas to counteract the relentless cooling, maintaining it at its multi-million-degree equilibrium. The question of what provides this precise and powerful heating has become one of the great detective stories in cosmology. The prime suspect in this cosmic mystery is the supermassive black hole that resides at the heart of the cluster's central galaxy. We now understand that these gravitational monsters are not just passive sinks. They can be incredibly active and influential engines. The leading theory, known as AGN feedback, proposes a delicate balancing act. As some of the hot intracluster gas does manage to cool and flow inward, a fraction of it eventually feeds the central supermassive black hole. This influx of material can trigger violent activity, causing the black hole to flare up as an active galactic nucleus, or AN. In this state, the black hole doesn't just consume matter. It also blasts titanic jets of energy and superheated plasma back out into the surrounding cluster environment. These jets create enormous bubbles and cavities in the X-ray gas, visible in detailed observations, which then buoyantly rise through the plasma, stirring it, creating shock waves, and ultimately depositing vast amounts of heat. It's a cosmic thermostat. As gas cools and falls in, it triggers the black hole to turn on and heat the surrounding medium, which then shuts off the fuel supply to the black hole, allowing the cycle to begin anew. While AGN feedback is a compelling solution, the unique conditions of the Coma cluster add a fascinating twist. Unlike many other bright X-ray clusters, Coma does not possess a single, dominant central galaxy with an overwhelmingly powerful AGN. Its core is more complex, with multiple giant ellipticals vying for dominance. This has led scientists to investigate whether other, more distributed heating mechanisms might also be at play. The sheer motion of galaxies through the plasma, for instance, could generate widespread turbulence and heat, much like a spoon stirring a hot cup of coffee keeps it warm. Furthermore, the relentless gravitational pull of the entire cluster continuously does work on the gas as it slowly collapses, converting gravitational potential energy into thermal energy. It's possible that in a massive, mature cluster like Coma, a combination of these effects, AGN outbursts, gravitational heating, and turbulent stirring, works in concert to provide the necessary energy, creating a stable, hot atmosphere that has resisted a catastrophic cooling flow for billions of years. This multi-source solution explains why the cluster remains in a precarious balance, Its galaxies starved of new fuel not by a single tyrant, but by the orchestrated physics of the entire metropolitan environment. This cooling flow problem is one of the most significant and enduring puzzles in modern astrophysics because it strikes at the heart of our understanding of energy balance in the universe. The logic was, and still is, compelling in its simplicity. Think of a steaming cup of coffee sitting on a table in a cold room. The coffee, being much hotter than its surroundings, will inevitably lose heat. It radiates energy, its molecules slow down, and it gradually cools toward room temperature. The hot, dense gas at the heart of a massive cluster like Coma is in a similar, albeit vastly more extreme, situation. It exists in the cold vacuum of space, and it is glowing fiercely in X-rays. This glow is the energy it is losing. Just like the coffee, it should be cooling down. The mathematics suggested that in the densest central regions, this gas should cool from tens of millions of degrees down to temperatures where it could form molecules and eventually stars in a relatively short time, cosmologically speaking. Astronomers calculated that this should result in a veritable downpour of cold gas flowing into the cluster's center, with potential star formation rates of hundreds, even thousands, of solar masses every single year. They expected to see central galaxies buried in colossal starbursts, shining with the brilliance of billions of newborn stars, but when they looked, they found a cosmic drought. The coffee was still steaming hot, defying all expectations, as if an invisible hand was holding a heater beneath the cup. The leading theory that emerged to solve this paradox is as elegant as it is violent, centering on the most destructive objects in the universe, supermassive black holes. This concept, known as AGN feedback, posits a dynamic and self-regulating cycle. The idea is that while the vast majority of the gas is kept from cooling, a tiny, residual amount does manage to cool and trickle inward toward the central supermassive black hole. This trickle of fuel is enough to awaken the sleeping giant, triggering an outburst of energy as the black hole becomes an active galactic nucleus, or AN. But rather than consuming all the material, these cosmic engines are incredibly messy eaters. They channel immense power into launching jets of relativistic particles and radiation that punch far out into the surrounding hot gas. These jets inflate gigantic, buoyant bubbles in the X-ray plasma, which rise through the cluster atmosphere like colossal hot air balloons. The process of inflating these bubbles, along with the powerful shock waves they generate, does two critical things. It physically pushes the hot gas outward, and it transfers a tremendous amount of energy back into it, reheating the medium and effectively shutting down the very cooling flow that was feeding the black hole in the first place. It's a brilliant cosmic thermostat, a self-correcting loop that prevents the system from either freezing into a starburst or overheating into chaos. However, while AGN feedback is a powerful and necessary ingredient, the unique character of the Coma cluster forces us to ask whether it is the only explanation operating here. Coma is what astronomers call a cool core cluster that doesn't behave like one, or perhaps a cluster in transition. Unlike many other massive clusters that show clear, dramatic signs of a single, dominant AGN at their heart, with obvious jets and bubbles, Coma's core is more democratic and chaotic. It lacks a single, overarching central galaxy with a clearly dominant supermassive black hole calling all the shots. Instead, its core is populated by several giant ellipticals, like NGC 4889 and NGC 4874, each with its own black hole, all jostling for position in a gravitational dance. This has led scientists to suspect that in an environment as complex and turbulent as Coma, other, more distributed heating mechanisms are likely also contributing to the prevention of a cooling flow. One such mechanism is shear gravitational heating. As the cluster continues to slowly assemble and evolve over billions of years, the relentless pull of its total mass, dominated by dark matter, is constantly doing work on the gas. Imagine the intracluster medium as a vast atmosphere being slowly compressed by the cluster's gravity. This continuous compression converts gravitational potential energy directly into thermal energy, providing a steady background heat source that keeps the overall temperature of the gas ferociously high. Furthermore, the frantic motion of thousands of individual galaxies through this plasma acts like an immense stirring mechanism. Each galaxy, as it plows through the thin gas at supersonic speeds, creates turbulent wakes and shocks, much like a speedboat churning up the water behind it. This widespread, chaotic motion distributes energy throughout the core, preventing the gas from settling, quieting down, and cooling efficiently. In this view, the absence of a cooling flow in Coma may not be due to a single AGN's outbursts, but to the combined orchestra-like effect of gravitational heating, turbulent stirring, and occasional AGN feedback from multiple sources. This multifaceted solution paints a picture of a cluster whose internal energy balance is maintained by the symphony of its own dynamic structure, a delicate equilibrium that has, for reasons we are still deciphering, successfully resisted a catastrophic cooling event for most of its existence. Amidst the grand-scale dramas of dark matter and colliding galaxies, there are also mysteries unfolding on a more intimate, yet equally spectacular stage: the lives and deaths of individual stars. Nestled within the Coma Cluster galaxy known as IC 4051, astronomers witnessed one of the most volatile and unpredictable events the stellar world has to offer: a titanic outburst from a luminous blue variable star. These are not ordinary stars, they are cosmic behemoths, hypergiants so massive and unstable they exist on the very brink of catastrophe. To find such a star in the quiet, red, and dead environment of the Coma Cluster is surprising in itself, but to catch it in a violent act of self-destruction opens a fascinating window into how extreme environments can influence the most dramatic stellar lives. Luminous blue variables, or LBV, are among the most massive and luminous stars known. Imagine a star so colossal it could dwarf our entire solar system, burning with a ferocious blue-white intensity millions of times brighter than our Sun. They are the rock stars of the cosmos, brilliant, glamorous, and notoriously unstable. Their immense gravity struggles to contain their own tremendous radiation pressure, causing them to wobble precariously on the edge of equilibrium. This leads to periods of extreme instability where they don't just gently swell and contract. They experience colossal eruptions, violently ejecting huge shells of their own outer layers into space. The outburst witnessed in IC 4051 was precisely this kind of event, a star essentially turning itself inside out, temporarily increasing its brightness to an almost incomprehensible degree and casting off a significant fraction of its own mass. This single stellar tantrum released more energy than our Sun will emit over tens of thousands of years. The sheer unpredictability of these stars is a central part of the mystery. Unlike the steady, predictable pulse of a Cepheid variable or the clean, final act of a supernova, the eruptions of luminous blue variables seem to follow no set schedule or clear trigger. They are capricious and spontaneous. An LBV can spend decades or even centuries in a quiet, stable phase, only to suddenly and without warning ignite into a spectacular outburst that reshapes its immediate surroundings. This makes catching one in the act a rare and precious event for astronomers. The outburst in IC 4051 was a fleeting cosmic flashbulb, a transient event that, had we not been looking at the right place at the right time, would have vanished from the record without a trace. This inherent unpredictability forces us to ask what exactly tips these stars over the edge. Is it an internal instability, a buildup of radiation pressure that finally blows the lid off? Or could external factors in their environment play a crucial role in triggering these stellar upheavals? This is where the unique context of the Coma Cluster becomes critically important. The environment within a massive galaxy cluster is far from peaceful. Stars, even giants like this LBV, are not isolated. They are subject to the relentless gravitational tides and pressures of their surroundings. For a star in IC 4051, orbiting within the dense core of the Coma Cluster, the experience is profoundly different from that of a similar star in an isolated field galaxy. The galaxy itself is constantly being jostled and harassed by its neighbors, its internal structure stirred by repeated gravitational encounters. This raises a compelling and complex question. Could the unique environmental pressures of the cluster have directly influenced this star's violent outburst? One theory suggests that the tidal forces exerted on the galaxy, and by extension on the star itself, could have acted as a catalyst. As IC 4051 moves through the cluster core, the differential gravitational pull from nearby massive galaxies could create subtle but significant stresses within the star. Think of it as a constant, low-frequency vibration running through the entire galactic system. For a star already teetering on the edge of instability, this persistent external jostling could be the final nudge that precipitates a massive eruption, much like how a subtle tremor can trigger an avalanche on a precariously balanced mountainside. The cluster environment, in this view, doesn't just quench star formation. It might also actively provoke the most massive stars to explode prematurely. Another possibility involves the galaxy's history of gas stripping. We know that ram pressure stripping can remove the diffuse gas reservoir from a galaxy, but what about the more immediate environment of a massive star? If the LBV in IC 4051 was surrounded by a cocoon of gas and dust, material shed from previous, smaller eruptions, the intense pressure from the intracluster medium could have compressed or distorted this cocoon. This sudden change in the star's immediate environment, the pressure on its stellar wind or its circumstellar material, could have altered the flow of energy and triggered a runaway instability. The outburst then wouldn't be purely an internal event. It would be a response to a drastic change in its external pressure bath, a stellar panic attack induced by the cluster's harsh conditions. The mystery of the luminous blue variable in IC 4051 ultimately transcends this single star. It challenges our understanding of stellar evolution in extreme environments. Our models for how these massive stars live and die are largely built on observations of them in relative isolation. The Coma Cluster event forces us to consider that the life story of a star, especially a volatile one, may be co-authored by its galactic neighborhood. The cluster's gravity, its intergalactic wind, and its turbulent history may all be silent partners in dictating the timing and violence of a star's final act. This single, brilliant flash of light in a distant galaxy is more than just a stellar outburst. It is a unique experiment showing us that even the most fundamental processes in astronomy cannot be fully understood without considering the vast and complex stage upon which they are set. Just when we think we have a handle on the complex dance of galaxies within the Coma Cluster, we encounter evidence of movement so extreme they seem to defy the very gravity that binds the cluster together. We are now looking at the astonishing and unexplained phenomenon of high-velocity galaxy ejections. Picture a galaxy, a system of billions of stars, being flung out from the cluster core like a stone from a slingshot, traveling at speeds so tremendous it could potentially escape the cluster's gravitational grasp entirely. These aren't just galaxies moving quickly, they are cosmic projectiles on a one-way trip into the void. The question is, what kind of cosmic catapult could possibly impart such an immense velocity to an object of such staggering scale? The most plausible explanation for these dramatic expulsions involves a complex gravitational dance between multiple massive bodies, a process known as a three-body interaction. Imagine two of the cluster's supergiant elliptical galaxies, each with a mass of trillions of suns, engaged in a slow, close gravitational waltz. If a smaller, third galaxy happens to wander too close to this binary pair, it can become entangled in their gravitational field. In a precise and rare alignment, the interloper can steal a tremendous amount of orbital energy from the duo. The two large galaxies, now bound more tightly together, sacrifice some of their own kinetic energy, which is then transferred to the smaller galaxy, accelerating it to a ferocious speed and launching it away on a new high-velocity trajectory. It's a gravitational slingshot effect, but on a scale that is almost unimaginable, where the engines of acceleration are entire galaxies themselves. While the three-body interaction is a sound theoretical mechanism, its application within the dense core of the Coma Cluster presents a significant puzzle. The sheer number of high-velocity ejections we observe, or at least infer from the peculiar motions of galaxies on the cluster's outskirts, seems higher than our simulations would predict. The central region is crowded, but for this specific energy-transferring interaction to occur so effectively, the timing and alignment have to be just right. It's a cosmic game of billiards where the cue ball must hit two other balls in a perfect sequence to achieve a breakaway shot. The frequency of these events suggests that either we are witnessing an unusually active period in the cluster's dynamical history, or there are other, even more powerful mechanisms at work that we have not yet accounted for. This leads to a more speculative but fascinating possibility. Perhaps the gravitational slingshot is not being performed by visible galaxies alone. What if the primary players in these interactions are not the stars we see, but the immense invisible clumps of dark matter that are believed to dominate the cluster's mass? If the dark matter halo of the Coma Cluster is lumpy and complex, with dense subhalos that lack bright stars, a close encounter between a visible galaxy and one of these massive dark objects could provide the gravitational kick needed for ejection, leaving no visible trace of the interaction that launched it. This idea pushes our understanding of the cluster's hidden structure to its limits, suggesting that the true dynamics of this cosmic metropolis are dictated by an unseen architecture we are only beginning to map. If the high-velocity ejections represent the cluster violently expelling some of its members, then our next mystery shows the cluster nurturing something that, by all rights, should not exist. In the vast and varied population of the Coma Cluster, astronomers have made a startling discovery within its smallest galactic residents, dwarf galaxies that harbor supermassive black holes of impossible proportions. This is a direct challenge to one of the most established relationships in modern astronomy, the scaling relation between a galaxy and its central black hole. In the local universe, we observe a clear and tight correlation. The more massive a galaxy's central bulge of stars, the more massive its central black hole tends to be. It's a partnership that suggests galaxies and their black holes grow together, co-evolving over billions of years. A typical dwarf galaxy, with a sparse collection of a few billion stars, should host a correspondingly modest central black hole, perhaps weighing in at a few thousand to a few 100,000 solar masses. But in the Coma Cluster, we find dwarfs that break this rule spectacularly. These galaxies, small and faint, contain black holes that are millions, sometimes even billions, of times the mass of our Sun, monsters that belong in galaxies 100 times their size. The existence of these overmassive black holes forces a complete re-evaluation of how the smallest galaxies form and evolve, especially within the high-pressure environment of a cluster. One compelling theory is that we are looking at the stripped-down cores of what were once much larger galaxies. Imagine a normal-sized spiral galaxy falling into the Coma Cluster long ago. Over eons, as it repeatedly passed through the dense cluster core, the relentless processes of ram pressure stripping and galaxy harassment physically tore away its outer layers, the diffuse halo, the delicate spiral arms, and vast reservoirs of gas. What remains is just the galaxy's central bulge and its core, a compact and dense survivor. Since the supermassive black hole resides in this central, tightly bound region, it remains largely unaffected by the stripping process. The galaxy is skinned alive, leaving behind a dwarf-sized galaxy with the beating heart of a giant. These objects, known as stripped nuclei or ultra-compact dwarfs, could explain why the black hole appears so disproportionately large, we are not seeing the original galaxy, but only its resilient black hole-hosting core. Another, more revolutionary idea is that these black holes formed first, acting as primordial seeds of incredible mass in the early universe. In the standard model of cosmic evolution, the first black holes are thought to have formed from the collapse of the very first stars, creating seeds of only a few dozen solar masses. These would then grow over time through mergers and accretion. But if the seeds themselves were already immense thousands or even millions of solar masses from the very beginning, they could easily explain the massive black holes we see in small galaxies today. The question then becomes, how could such a heavy seed form? The conditions in the early universe might have allowed for the direct collapse of enormous gas clouds into black holes, bypassing the star formation stage entirely. The intense radiation fields and rapid mergers in the nascent Coma Cluster protostructure could have been a perfect nursery for these direct collapse black holes, planting monstrous seeds in small galaxies that never grew to match their central engines. The cluster environment, therefore, may have preserved these ancient relics, fossils from an era when the rules of galaxy formation were fundamentally different. Together, the phenomena of high-velocity ejections and overmassive black holes in dwarfs paint a picture of the Coma Cluster as a place of extreme and transformative dynamics. It is an environment that can violently expel entire galaxies into the intercluster void, while simultaneously whittling others down to their most essential cores, revealing the primordial monsters that lurk within. One process speaks to the immense forces at play in the present-day cluster, the other to a deep and hidden history written in the hearts of its smallest members. These are not separate mysteries, but two sides of the same coin, showing us that in this cosmic metropolis, the lives of galaxies, from the mightiest giants to the most humble dwarfs, are shaped by forces of creation and destruction that we are only just beginning to comprehend. Building on the theme of dark matter's elusive nature, we arrive at two phenomena that probe its existence in profoundly different ways, one by its absence of light, and the other by its undeniable distortion of light. First, we have the hunt for the ultimate cosmic ghost, a dark galaxy. The idea itself sounds like science fiction, an island in space with the mass of a full-fledged galaxy, but utterly devoid of stars. No glittering spiral arms, no brilliant core, no glowing clouds of gas, just a massive, invisible clump of dark matter moving through the cluster under its own gravity. Finding such an object is one of astronomy's greatest challenges, because how do you see something that emits no light at all? The primary method is to look for the subtle, telltale signatures of its influence. Astronomers search for rotating clouds of hydrogen gas that exhibit the gravitational signature of a massive, unseen object holding them together. They look for unexplained distortions in the fabric of space-time, or even for the rare occasions when such a dark object might pass in front of a distant star, causing a brief, telltale flicker through a phenomenon called microlensing. Within the Coma Cluster, this search has yielded several tantalizing candidates. These are often identified as isolated clouds of hydrogen gas that are spinning far too rapidly to be held together by their own negligible visible mass. The gravity required to keep these clouds from simply flying apart is immense, pointing to the presence of a massive dark matter halo. One of the most compelling aspects of this search is that it tests a key prediction of the prevailing cosmological model, which suggests that the universe should be teeming with far more small, dark matter halos than we see visible dwarf galaxies. These dark galaxy candidates could be the missing pieces of that puzzle, the myriad small halos that, for some reason, never manage to attract or retain enough gas to light up with stars. Perhaps they were born in a region of the early universe that was already too devoid of normal matter, or maybe the intense radiation from neighboring quasars in the cluster's violent past sterilized them, preventing star formation from ever beginning. Each candidate is a potential confirmation of a fundamental cosmic prediction, a shadowy counterpart to the bright galaxies we see, and their confirmed existence would reshape our understanding of how structures form across the scale of the universe. Yet, the evidence for these dark galaxies remains circumstantial and hotly debated. The central challenge is that other explanations can often account for the observations. What appears to be a cohesive, rotating dark galaxy could, in fact, be a tidal dwarf galaxy, a clump of gas and a few stars that was torn away during a galactic collision and is now dynamically behaving in a way that mimics a more massive object. Alternatively, it could simply be a filament of the cosmic web, a tendril of gas that is being stretched and stirred by the cluster's gravity, giving the false impression of a coherent, rotating body. Proving that a candidate is truly a dark galaxy requires ruling out all these other possibilities, a task that demands multiple, independent lines of evidence. The hunt continues, a meticulous process of elimination in the hope of finding that one pristine example of a galaxy that is all skeleton and no flesh, a perfect embodiment of dark matter's dominant yet invisible role in the cosmos. While the search for dark galaxies is a hunt for objects defined by their lack of light, our next phenomenon uses light itself as a tool to reveal the invisible. Gravitational lensing, the bending of light by mass as predicted by Einstein, is the most powerful tool we have for mapping dark matter. In the Coma Cluster, this technique has been employed to create detailed mass maps, revealing where the true gravitational weight lies. For the most part, these maps align with our expectations. The bulk of the mass is concentrated in the cluster's core and follows the general distribution of the thousands of galaxies we can see. However, scattered across these detailed maps are curious anomalies, pockets and arcs where the lensing signal is stronger or stranger than it should be. These are the gravitational lensing anomalies, and they are the fingerprints of something unexpected in the dark matter's arrangement. These anomalies manifest in several ways. Sometimes a background galaxy appears more distorted or sheared than the visible mass in that part of the cluster can account for. It's as if an invisible lens, far more powerful than it should be, is embedded within the larger cluster lens. Other times, astronomers find multiple, duplicated images of a single distant quasar, but the arrangement and brightness of these images don't match the predictions from models based solely on the visible matter. This indicates that the dark matter is not smoothly distributed, as is often assumed in simpler models, but is instead clumped and substructured in ways we did not anticipate. These clumps are the gravitational equivalents of hidden reefs beneath the surface of the ocean, warping the passage of light in subtle but detectable ways. They hint at a complex, lumpy architecture within the cluster's main dark matter halo, a universe of invisible substructure that we are only just beginning to sense. The implications of these lensing anomalies are profound. They challenge the standard model of cold dark matter, which predicts a certain level of substructure, but perhaps not with the specific properties we are observing. If the dark matter is too clumpy, or if the clumps are too dense, it might suggest that dark matter particles have properties beyond the simple, collisionless nature we assign to them. Perhaps they can interact with each other through some unknown force, creating more complex gravitational landscapes. Alternatively, these anomalies could be pointing towards something even more exotic. Some physicists have proposed that what we are seeing is evidence for topological defects in the fabric of space-time, cosmic strings or domain walls left over from the early universe that create intense, localized gravitational fields. While still speculative, this idea illustrates how anomalies in a distant galaxy cluster can force us to consider fundamental physics at its most extreme. Each unexplained distortion in the light from a distant galaxy is a potential clue, a ripple in space-time that whispers secrets not just about the dark matter in Coma, but about the very nature of the cosmos. As we peel back the layers of the Coma Cluster, we encounter a population of cosmic objects that defy simple classification, existing in a strange middle ground between star clusters and true galaxies. These are the ultra-compact dwarf galaxies, or UCT. To the untrained eye, they might be dismissed as a simple, bright star or a faint smudge, but they are in fact dense spheres containing tens of millions of stars, all packed into a region only about 200 light-years across. If you were to place one at the location of the Omega Centauri cluster in our own Milky Way, it would shine nearly as brightly as the full moon in our night sky. Their very existence presents a classic nature versus nurture puzzle for astronomers. Are these objects born this way, as super-sized versions of the globular clusters we see orbiting most galaxies? Or are they the battered, stripped-down remains of something much larger, the surviving hearts of galaxies that were torn apart by the cluster's ferocious gravitational tides? The leading theory for their origin is a dramatic one, painting a picture of galactic violence on an epic scale. It suggests that many UCDs are the luminous, stripped nuclei of smaller galaxies that wandered too close to one of the cluster's giant ellipticals. Imagine a small spiral or lenticular galaxy with a bright, compact core falling into the dangerous inner regions of the cluster. As it swings past a behemoth like NGC 4889, the immense tidal forces act like a cosmic grater, systematically peeling away the galaxy's outer layers, its halo, its disk, and its sprawling spiral arms. What remains after this gravitational shredding is just the galaxy's central bulge, the one part of the galaxy that was dense enough and gravitationally bound enough to resist being torn apart. This surviving nucleus, now orphaned from its original galactic body, continues to orbit the cluster as an ultra-compact dwarf. Supporting this violent history, spectroscopic studies reveal that many UCDs contain multiple generations of stars and have complex chemical compositions, much like the cores of larger galaxies, rather than the single, pristine stellar populations typical of most globular clusters. They are the celestial equivalent of a dinosaur's femur found in a desert, a dense, durable relic of a much larger creature that has long since vanished. Yet, the alternative theory holds that at least some UCDs could be genuine primordial objects, simply forming as exceptionally massive star clusters from the very beginning. In the chaotic early universe, regions of extraordinarily dense gas could have collapsed directly into these superstar clusters without ever being part of a larger galactic disk. The crowded environment of the nascent Coma Cluster, with its frequent galactic interactions and immense gas clouds, would have been a perfect incubator for such monstrous clusters. The mystery deepens because both pathways could be operating simultaneously. The Coma Cluster seems to be a factory that both creates UCDs from scratch and forges them through destructive processes, leaving us to untangle a population of objects with dual, overlapping origins. This makes them critical yet confusing puzzle pieces in our understanding of how stellar systems assemble and evolve under extreme conditions. This theme of creation through destruction leads us directly to our next phenomenon, a process that seems to defy the traditional rules of galaxy formation. While the cluster's tides are busy tearing galaxies apart to create UCDs, those same titanic collisions are also giving birth to entirely new galaxies in a process known as tidal dwarf galaxy formation. This is a cosmic phoenix rising from the ashes, a rare instance of genesis emerging from chaos. When two large galaxies graze or collide, their mutual gravitational pull can draw out immense tidal tails, long streamers of gas, dust, and stars that are flung far out into intergalactic space. Within these ejected rivers of material, the densest knots of gas can collapse under their own gravity, cooling and fragmenting to ignite bursts of new star formation. These collapsing knots can eventually become self-gravitating, independent objects, new, dwarf galaxies born not from the collapse of a pristine dark matter halo, but from the recycled debris of a galactic wreck. The existence of these tidal dwarfs in the Coma Cluster is both fascinating and perplexing. On one hand, their formation is a direct and observable prediction. we see the long, graceful arcs of tidal debris and the bright, blue knots of young stars within them, clear evidence of ongoing creation. However, their long-term survival in the cluster's harsh core is the real mystery. A newly formed tidal dwarf is a fragile thing. Unlike traditional galaxies, it is born with little to no dark matter, since the dark matter halos of the parent galaxies are too diffused to be pulled out into the tidal tails. This means a tidal dwarf is held together almost solely by the gravity of its visible stars and gas, making it exceptionally vulnerable. In the rough and tumble environment of the Coma Cluster, such a bare galaxy should be easily torn apart by the first close encounter with a massive neighbor or shredded by the relentless ram pressure stripping of the intracluster medium. The fact that we observe candidate tidal dwarfs in the cluster, some even located far from the obvious debris of a recent collision, forces a profound question. Can these dark matter, poor galaxies actually survive for billions of years, or are we merely seeing temporary, fleeting structures destined for a quick demise? Their potential longevity would challenge our understanding of galactic stability, suggesting that perhaps the sheer density of stars in some of these objects can provide enough gravitational glue to hold them together, even without a dark matter anchor. Each one we find is a test case, a natural experiment that probes the minimum requirements for a gravitationally bound island of stars to persist in the most hostile of environments. They are living proof that the cluster is not just a place of death and decay, but also a nursery for a strange and tenuous new form of galactic life. Finally, we come to a mystery of pure cosmic excess, a phenomenon of sheer abundance that surrounds the cluster's most massive residents. The giant elliptical galaxies at the heart of the Coma Cluster, like NGC 4889 and NGC 4874, are not just surrounded by a few globular clusters, they are enveloped in a veritable blizzard of them. A typical spiral galaxy like our Milky Way possesses about 150 of these ancient, dense star clusters. The Coma giants, however, are each attended by many thousands, some estimates reaching as high as 15 to 20,000 globulars per galaxy. This staggering overabundance presents a clear puzzle. How did these galaxies acquire such an immense entourage of ancient stellar systems? The answer appears to be tied directly to the cluster's long and violent history of galactic cannibalism. Globular clusters are thought to form primarily during intense, initial bursts of star formation, and they are incredibly durable, acting as cosmic survivors. As smaller galaxies fall into the cluster and are devoured by a central giant, their own globular cluster systems are not destroyed. Instead, they are stripped away and added to the giant's growing collection. Each galaxy consumed is like a delivery of more globulars, and over billions of years, the central ellipticals have grown fat on a diet of their smaller neighbors, their globular cluster counts swelling with every merger. This process, known as hierarchical assembly, provides a general framework for understanding the overabundance. The giants are the ultimate cosmic collectors, their swarms of globular clusters serving as trophies of their destructive past. However, the sheer scale of the overabundance in Coma suggests that this process might have been even more efficient than our models predict. It hints that the early Coma protocluster was an exceptionally fertile ground for the formation of globular clusters themselves. Perhaps the frequent, gas-rich mergers in the cluster's youth triggered universe-wide starbursts that produced globular clusters at a rate far exceeding what we see in more quiescent environments. Another possibility is that many of the objects we now classify as ultra-compact dwarfs were originally mistaken for globular clusters, inflating the numbers, but more refined observations continue to show a genuine surplus. This overabundance is more than just a record of past violence. It is a cosmological measuring stick. By counting these ancient clusters, astronomers can effectively weigh the entire assembly history of the cluster, using the glittering swarms around the central galaxies to reconstruct the sequence of mergers and acquisitions that built the Coma Cluster into the colossal metropolis we see today. They are the enduring witnesses to a history of galactic conquest on a scale that is almost impossible to comprehend. But if we shift our perspective from the individual movements of stars to the grand ballet of entire galaxies, we uncover a pattern of motion that is just as mystifying. Galaxies within the Coma Cluster are not simply swarming in a chaotic, random buzz like bees around a hive. Instead, their velocities reveal a distinct and unexpected organization, a coordinated flow in certain directions that astronomers call an anisotropic velocity distribution. This discovery challenges one of the most fundamental assumptions in cosmology, that massive, ancient clusters like Coma should be in a state of virial equilibrium, a stable balance where the kinetic energy of their members is evenly distributed in all directions. The fact that we see a preferred direction of motion tells us that Coma's story is far from over. It is a dynamic system still settling from a turbulent past, and the echoes of that past are written in the trajectories of its thousands of galaxies. To understand why this anisotropy is so surprising, picture a cloud of gas in a sealed container. After a while, the molecules will bounce around in every possible direction with equal probability. Their motion becomes isotropic, perfectly even. For a galaxy cluster that has existed for billions of years, we expect a similar outcome. The relentless gravitational interactions between galaxies should have, over immense timescales, randomized all their orbits, erasing any memory of the specific direction from which they fell into the cluster. The presence of a strong anisotropic signal is therefore like finding that the molecules in our gas cloud are all drifting preferentially to the left. It's a clear sign that the system has not had enough time to fully mix, that a major disruptive event occurred relatively recently in its history, and the cluster is still vibrating like a struck gong. The most compelling explanation for this coordinated motion points to a dramatic and colossal merger event in the cluster's recent past. We are not talking about two small galaxies colliding, but the monumental merging of two or more entire galaxy groups or subclusters, each the size of a small city of galaxies in its own right. Imagine two vast swarms of galaxies, each with its own trajectory and momentum, slamming together. The galaxies from the infalling subcluster wouldn't just stop, they would tend to continue moving along the general axis of the collision, creating a stream or a flow within the larger, merged system. Detailed computer simulations show that after such a major merger, it can take many billions of years for the anisotropic motions to finally dampen out and for the cluster to relax into a truly random, isotropic state. The fact that we still detect this anisotropy in Coma suggests we may be witnessing the aftermath of one of the largest cosmic collisions ever observed, an event that is still shaping the cluster's internal dynamics today. This merger scenario isn't just a theoretical guess, it aligns beautifully with other pieces of the puzzle we find scattered throughout Coma. The cluster's complex and irregular X-ray emission, for instance, shows asymmetries and substructures that look like the ripples from a massive impact. The very presence of two supergiant elliptical galaxies, NGC 4889 and NGC 4874, so close to the center, is itself a classic signature of a past merger, as they could be the former central galaxies of two distinct clusters that have now coalesced. The anisotropic velocities of the galaxies provide the final, crucial piece of dynamical evidence, the smoking gun that reveals the direction and nature of that ancient collision. It allows astronomers to rewind the cosmic clock, to run simulations backward and reconstruct the possible trajectories of the merging subclusters, piecing together a billion-year-old crime scene. However, an alternative and perhaps even more intriguing possibility exists. What if the anisotropy is not a temporary relic of a single merger, but a permanent feature of the cluster's environment? The Coma Cluster is not an isolated island. It lies at the heart of the larger Coma supercluster, a vast web of galaxies and galaxy groups that are all gravitationally connected. It is possible that the anisotropic flow we see is not an internal vibration but a sustained river of motion, a continuous infall of galaxies from the surrounding cosmic filaments. In this view, the cluster is constantly being fed by new galaxies streaming in along the great dark matter highways of the universe, and this ongoing accretion maintains a preferred direction of motion, preventing the cluster from ever reaching a perfectly relaxed state. The anisotropy, then, becomes a real-time window into the cluster's growth, showing us how it is still gathering mass from the cosmic web that birthed it. This phenomenon forces a significant revision of our basic assumptions. For decades, cosmologists have used the properties of relaxed galaxy clusters as cosmic measuring tools. By assuming they are in equilibrium, we can use their size, mass, and galaxy population to estimate fundamental cosmic parameters and test our models of the universe's evolution. The clear anisotropy in Coma tells us that this assumption of equilibrium is not always safe. It serves as a critical reminder that these colossal structures are living, breathing entities with complex histories, and that applying simple, uniform models to them can lead us astray. The coordinated motion of Coma's galaxies is more than just a curious dynamical fact. It is a profound cautionary note, reminding us that the universe's largest structures often hold onto the memories of their violent origins for far longer than we ever imagined. Now consider the possibility of witnessing a stellar explosion that actually happened millions of years ago, a cosmic ghost replaying its own death across the eons. This is the strange and beautiful concept of a light echo, and the search for one within the Coma cluster opens a unique window into its explosive past. Imagine a supernova, a star ending its life in a cataclysm so brilliant it can outshine its entire host galaxy for a few fleeting weeks. The initial flash of light from that detonation races outward at the speed of light, traveling directly toward any observers in its path. But that is only the first act. That brilliant pulse of radiation also floods out in all other directions, illuminating vast, dark clouds of interstellar dust that may be light years away from the explosion itself. When the light finally strikes these cosmic dust bunnies, it doesn't just vanish, it scatters, reflecting off the tiny particles. This reflected light then begins its own journey toward us, but because it took a longer, indirect path, it arrives much later than the direct light from the original event. The result is an illusion of an expanding ring of light, a shimmering apparition that appears to grow in the sky years or even centuries after the supernova itself has long since faded from view. It's not a new explosion, it's the universe's own delayed broadcast, an echo of a long silent cosmic shout. Detecting such a subtle phenomenon within the dense heart of the Coma cluster presents an immense technological and observational challenge. The primary obstacle is the sheer distance and the cluster's crowded nature. The light we receive from Coma is already incredibly faint, having traveled for over 300 million years. A light echo would be fainter still, a ghostly shimmer superimposed on the already diffuse light of the galaxy it resides in. Distinguishing this faint, expanding ring from the background glow of billions of other stars requires exquisitely sensitive instruments and a painstaking process of comparing images taken years or decades apart. Astronomers must look for subtle changes in the brightness and structure of specific patches of light within a galaxy, searching for a ring-like feature that appears to be moving outward at an impossible speed faster than light. Of course, it's not truly moving faster than light. It's an illusion created by the geometry of the echo, but its apparent expansion can be dramatic. Adding to the difficulty is the fact that the dust clouds responsible for the echo are not perfect mirrors. They are lumpy, complex structures, which means the echo itself may not form a perfect, photogenic ring, but rather a more fragmented and irregular shell of light, making it even harder to spot against the complex backdrop of a distant galaxy. Yet, the scientific payoff for successfully identifying a light echo in Coma would be extraordinary, offering us a form of time travel archaeology for stellar events. For starters, it would give us a direct and precise measurement of the distance to the supernova's host galaxy within the cluster. By studying the angular size of the echo ring and knowing the speed of light, astronomers can triangulate the physical distance to the dust cloud that is creating the reflection. This provides an independent and highly accurate yardstick for cosmic distances, helping to calibrate our maps of the universe on the largest scales. Furthermore, by analyzing the spectrum of the echoed light, breaking it down into its constituent colors, we can recover the original fingerprint of the ancient supernova. We could determine what type of star exploded, its chemical composition, and the precise mechanics of its explosion, all from an event that occurred before dinosaurs walked the Earth. This turns the echo into a cosmic forensic tool, allowing us to perform an autopsy on a star that died hundreds of millions of years ago, reconstructing the final moments of a stellar life that we never directly witnessed. The existence of such an echo would also illuminate the hidden structure of the galaxy itself. The way the light echo expands and evolves is dictated entirely by the three-dimensional arrangement of the dust clouds around the long-dead star. As the echo expands, it lights up successive shells of interstellar material, effectively giving us an X-ray vision of the galaxy's dark, dusty anatomy. We could map out the distribution and density of these clouds, understanding how the raw materials for future stars and planets are scattered throughout the galactic environment. It reveals the topography of the darkness, showing us the canyons and mountains of dust that would otherwise remain completely invisible to our telescopes. In this way, a single, ancient flash of light reflected back to us over cosmic timescales can tell two stories at once: the violent death of a star and the detailed structure of its home, providing a multidimensional glimpse into the history of a galaxy we can only observe as a single, faint smudge of light in the sky. Beyond the brilliant islands of individual galaxies, there exists a far more subtle and ethereal component to the Coma Cluster, a faint, pervasive glow that permeates the spaces between them. This is the diffuse intracluster light, a cosmic ghost light made of billions of stars that are no longer bound to any single galaxy, but instead float freely in the immense gravitational field of the cluster itself. If you could see it with the naked eye, it would appear as a faint Milky Veil, a soft luminosity connecting the brighter galactic dots into a single, cohesive structure. This isn't the intense X-ray glow of hot gas or the radio emission of energetic particles. This is the combined starlight of countless suns that have been torn from their homes and cast adrift in the intergalactic void. The existence of this light tells a story of profound violence, and its specific properties are like a forensic report detailing the cluster's most turbulent historical events. The central mystery of the intracluster light is one of origin and process. How exactly are these stars liberated from their galaxies on such a colossal scale? The primary mechanism is thought to be the same brutal gravitational forces that quench star formation and create ultra-compact dwarfs, galactic harassment and tidal stripping. As galaxies swing past one another at tremendous speeds, their mutual gravitational pull tugs and twists at their structures. Unlike the dense, tightly bound galactic cores, the outer regions of a galaxy, its halo of old stars and globular clusters are only loosely held by gravity. During a close encounter, these outermost stars can be pulled away like taffy, stretched into long streams that are eventually flung out into the cluster's gravitational well. Once free, they no longer orbit their parent galaxy. They begin to orbit the center of mass of the entire Coma Cluster, becoming permanent citizens of the intracluster space. The timescales involved in building up this faint glow are as immense as the process is destructive. The intracluster light is not the product of a single catastrophic event, but rather the accumulated debris from billions of years of relentless gravitational interactions. It is a slow mountain archaeological site where each generation of galactic collisions adds another thin layer of stellar dust to the overall glow. This gradual accumulation is precisely what makes the intracluster light such a powerful historical archive. The brightness, color, and distribution of this light act as a fossil record of the cluster's assembly. A brighter, more extensive intracluster glow suggests a long and violent history of frequent mergers and interactions, while a fainter, more centrally concentrated one might point to a common evolutionary path. In the case of the Coma Cluster, the intracluster light is both extensive and complex, indicating a past filled with dramatic mergers and a continual shuffling of its galactic population. What makes the intracluster light in Coma particularly intriguing is its specific distribution and composition. Detailed observations reveal that this ghostly glow is not smooth or uniform. Instead, it is clumpy and streaky, containing faint plumes, arcs, and tidal streams that can still be traced back to specific galactic encounters, even long after the event itself. It's as if we are looking at the lingering smoke trails from a series of cosmic explosions, their shapes preserved in the faint starlight. Furthermore, the color of this light, leaning toward the redder end of the spectrum, tells us that these exiled stars are predominantly old red giants. This makes perfect sense, as the stars most easily stripped from a galaxy are those in the extended ancient halo, not the younger blue stars typically found in the densely packed galactic disks. This color signature confirms that we are seeing the shreds of galactic halos, the outer vestiges of galaxies that have been systematically dismantled over cosmic time. The properties of this diffuse light are forcing astronomers to reconsider the intensity of the Coma Cluster's merger history. The sheer amount of intracluster starlight suggests that a significant fraction of the cluster's total stellar mass, perhaps as much as 20%, now resides outside of any recognizable galaxy. This is a staggering quantity of material, implying a level of galactic destruction far beyond what was previously estimated. It provides independent, compelling evidence for the major merger scenario we discussed with the anisotropic velocities. The faint streams and asymmetries in the intracluster light can be used to literally map the trajectories of past collisions, identifying which galaxies interacted and in what direction they were moving when they shed their stellar envelopes. This turns the diffuse glow from a simple curiosity into a dynamic tool for reconstructing the cluster's family tree, revealing which of the giant ellipticals we see today are the cannibalistic products of many smaller galaxies consumed in the distant past. The intracluster light is the final, fading testament to those lost galaxies, a memorial written in starlight to the violent events that shaped the cosmic metropolis we observe today. Drifting through the heart of the Coma Cluster, we find galaxies transformed into cosmic specters, their forms twisted into something both beautiful and tragic. These are the jellyfish galaxies, and they offer one of the most visually stunning examples of the violence inherent in this dense environment. A jellyfish galaxy appears exactly as its name suggests, a bright, compact body of stars, the head followed by long, flowing tendrils of gas and dust that can stretch for hundreds of thousands of light years, streaming out behind it like ghostly tentacles. This is not a serene, slow-motion process. It is the signature of a galaxy in the midst of a desperate struggle, fighting for its very life against an invisible and relentless force. The mechanism that creates these ephemeral shapes is a particularly brutal form of the ram pressure stripping we encountered earlier, but here it is operating at its most extreme. Imagine a spiral galaxy rich with cold, star-forming gas falling into the cluster core on a specific, punishing orbit, a trajectory that sends it screaming through the densest, hottest part of the intracluster medium at several million miles per hour. The pressure exerted by this thin, superheated plasma is overwhelming. It acts like a hurricane force wind, but one blowing through the near vacuum of space. This wind doesn't affect the stars themselves, which are too dense and tightly bound to be easily displaced. Instead, it targets the galaxy's lifeblood, the diffuse clouds of gas and dust that drift between the stars. This material is far more loosely held by the galaxy's gravity, and as the galaxy plunges forward, this gas is caught by the headwind, seized, and physically torn away. The result is that the galaxy is effectively being disemboweled, its star-forming material ripped out and left to trail behind it in those long, luminous tails. Within these tendrils, the stripped gas, now compressed and shocked by the process, can sometimes ignite bursts of new star formation, creating a cruel irony. The very act of destroying the galaxy's future fuel supply can trigger a final, brilliant flare of stellar birth within the tendrils themselves. What makes the jellyfish galaxies of Coma so mysterious, however, is not just their existence but their specificity. Why do we see these dramatic transformations in some galaxies while their neighbors, seemingly in the same environment, remain intact? The answer appears to lie in a delicate and fatal combination of factors, a cosmic perfect storm. The primary ingredient is the galaxy's orbital path. A galaxy on a highly radial, plunging orbit, one that takes it on a steep dive directly through the cluster's central core, will experience the full, brutal force of ram pressure stripping at its maximum intensity. It's the difference between wading through a calm pond and being hit by a fire hose. The journey matters immensely. A galaxy on a wider, more circular orbit might experience a gentler, more continuous stripping that doesn't produce the same spectacular tendrils, instead slowly suffocating the galaxy over a longer timescale. The internal structure and initial state of the galaxy itself are equally critical. A gas-rich spiral galaxy with a large, fluffy reservoir of hydrogen is a perfect candidate for becoming a jellyfish. Its fuel is abundant and easily removed. In contrast, a galaxy that has already been pre-processed, one that fell into a smaller group before joining the main cluster and had much of its gas stripped or consumed, arrives in Coma already gas-poor. It has little left to lose and thus won't develop the dramatic tails even on a punishing orbit. The orientation of the galaxy as it moves also plays a role. A galaxy that presents its disk face onto the direction of motion will have a much larger surface area exposed to the ram pressure, leading to more efficient and dramatic stripping, compared to one that is moving edge-on, which offers a narrower profile to the onslaught. This intricate interplay of trajectory, timing, and internal composition means that becoming a jellyfish is a specific and relatively short-lived phase in a galaxy's life. We are catching these objects in a fleeting moment of cosmic metamorphosis, a transitional state that might only last a few 100 million years before the galaxy is completely stripped of its gas and joins the silent, red, and dead population. The prevalence of these objects in Coma provides a unique and urgent laboratory for studying the most rapid and extreme form of galaxy evolution. Astronomers are intensely studying the star formation within the tendrils, seeking to understand how environmental pressures can trigger or quench the birth of stars in such unusual conditions. Furthermore, these galaxies act as natural probes, their streaming tails mapping out the density and flow of the otherwise invisible intracluster medium they are moving through. Each jellyfish galaxy is a living experiment, demonstrating in real time the destructive power of a cluster's environment and highlighting the precise conditions that can force a galaxy to reveal its own evisceration in a blaze of tragic and fleeting beauty. Their abundance in Coma suggests a particularly active and violent recent history, with a steady influx of new galaxies falling into the cluster core on devastating orbits, providing a continuous supply of victims for this remarkable transformation. As we witness the tragic beauty of jellyfish galaxies being stripped of their lifeblood, we must also acknowledge a force that stands in stark opposition, a force that doesn't remove material, but instead pushes it back with immense power, preventing the cluster from consuming its own future. This brings us to one of the most dynamic and visually spectacular relationships in the Coma Cluster: the mysterious correlation between radio galaxies and the colossal X-ray cavities that punctuate the hot gas. Imagine once more the brilliant X-ray glow that fills the cluster's core, a searing atmosphere of multimillion-degree plasma. Now, within that brilliant glow, picture vast, dark regions, enormous bubbles that appear to be empty, pushed out of the hot gas like holes in a cosmic Swiss cheese. These are the X-ray cavities, and they are not truly empty. They are filled with something else entirely, a superheated magnetized plasma that emits not in X-rays but in radio waves pouring from the hearts of active galaxies. The origin of these cavities is a story of cosmic violence on an epic scale, centered on the supermassive black holes that lurk in the cores of certain galaxies. When such a black hole is actively feeding on surrounding gas and dust, it doesn't consume all the material quietly. Instead, it can channel immense amounts of energy into launching two opposing, pencil-thin jets of charged particles that travel at nearly the speed of light. These jets, powerful and focused, scream out from the galactic center for tens of thousands of light years, eventually plowing into the thick atmosphere of the intracluster medium. When they hit this wall of hot gas, they don't simply bore through, they inflate. The jets dump their energy into the surrounding medium, pushing the X-ray emitting gas outward and creating gigantic, buoyant bubbles that rise slowly through the cluster atmosphere like colossal hot air balloons in a gravitational field. We see the evidence of this process clearly: a bright, active galaxy at the center of the cavity, often with radio telescopes revealing the jets that feed it, and the cavity itself appearing as a dark shadow in X-ray images, a void carved out by the black hole's incredible outburst. This connection is undeniable. The radio galaxy is the sculptor, and the X-ray cavity is its creation. But the deeper mystery lies not in the existence of this relationship, but in its precision and purpose. This is where we encounter the enigma of feedback. The prevailing theory is that this process acts as a self-regulating cosmic thermostat, a fundamental control mechanism for the entire cluster's evolution. The logic of the cooling flow problem dictates that the hot gas at the cluster's heart should be cooling rapidly, flowing inward and forming trillions of new stars. But it isn't. The supermassive black hole appears to be the reason why. As gas begins to cool and condense toward the center, some of that same gas inevitably falls onto the black hole, powering it up and triggering an outburst. The resulting jets then inflate cavities that do two critical things. They physically push the hot gas outward, and as they rise, they generate sound waves and shock fronts that travel through the intracluster medium, distributing their energy and reheating the gas. This heating counteracts the cooling, shutting off the fuel supply for both star formation and eventually for the black hole itself. It's a brilliantly balanced cycle. Cooling triggers heating, which then suppresses cooling. This feedback loop is thought to be the primary reason why central galaxies in clusters are not buried in runaway starbursts. However, the term feedback mechanism conceals a multitude of profound and unsolved problems. The first major puzzle is one of energy transfer. We can measure the total energy required to inflate these cavities. It's a staggering amount, often equivalent to the energy released by billions of supernovae. But how exactly is that energy transferred from the jets and cavities to the surrounding gas in a way that is so perfectly distributed and efficient? The cavities themselves are relatively clean and don't mix violently with the hot gas. They simply rise and drift. The leading idea is that their work is done through sound. As they buoyantly rise, they may generate powerful sound waves that ripple through the intracluster medium, like a bell ringing in a fog, and the dissipation of these waves gently heats the gas. Another possibility is that the bubbles create turbulence as they move, stirring the cluster's atmosphere and converting their kinetic energy into thermal energy. Yet, when astronomers run the numbers, they often find that the observed level of turbulence or the strength of the sound waves doesn't seem to fully account for the precise amount of heating required to balance the prodigious X-ray cooling. There appears to be a discrepancy in the accounting of energy. a missing link in the chain of how the black hole's fury is translated into a gentle, uniform warmth. A second, equally baffling problem is the incredible timing and precision of this feedback. The system is not in a constant state of eruption, it seems to pulse. The black hole switches on, inflates a pair of cavities, and then switches off for a period, only to reactivate when gas has had time to cool and accumulate once more. How does a black hole, an object defined by its immense gravity and relatively simple properties, regulate its own activity with such finesse? What is the sensor that tells it when to turn on and, just as importantly, when to turn off? Is it the rate of gas accretion onto the black hole itself, or is it influenced by larger-scale conditions in the cluster core? The mechanism that governs this duty cycle, the on and off switch for these universe-altering explosions, remains one of the most active and contentious areas of research in astrophysics. It suggests a level of self-regulation that is almost biological in its complexity, arising from the interplay of fundamental physics. Within the Coma Cluster, this mystery takes on a special character. Unlike some clusters with a single, dominant central galaxy clearly responsible for the feedback, Coma's core is a more democratic and chaotic environment. It hosts multiple giant ellipticals, each with its own supermassive black hole, and the X-ray cavity structure is correspondingly more complex. This raises the possibility that Coma is being heated by a committee of black holes rather than a single dictator. The feedback is not a simple, periodic outburst from one source, but a chorus of overlapping events from multiple AGN. This makes disentangling the cause and effect incredibly difficult. Is the heating we observe the result of a recent, large outburst from one black hole, or the accumulated effect of many smaller, frequent outbursts from several? Understanding how this collective feedback operates is crucial, because if our models cannot accurately reproduce how multiple AGN collectively regulate a cluster's temperature, then our entire understanding of galaxy cluster evolution may be missing a vital piece of physics. Ultimately, the correlation between radio galaxies and X-ray cavities is far more than a simple cause and effect. It is a window into how the most massive black holes in the universe communicate with and control their environment on a scale of millions of light years. It represents a fundamental coupling between the very small, the physics of accretion onto a black hole, and the very large, the thermodynamics of an entire galaxy cluster. The unsolved problems at the heart of this feedback mechanism touch upon plasma physics, gravity, and hydrodynamics in regimes we cannot hope to replicate in any laboratory on Earth. Each cavity is a fossil of a past eruption, and by studying their sizes, shapes, and distributions, astronomers are essentially reading the historical diary of the black holes in the Coma Cluster, a record of their past outbursts and their ongoing battle against the inevitable pull of gravity and cooling. This cosmic feedback loop is not just a fascinating puzzle, it is a critical process that has dictated the life and death of stars in the cluster for billions of years, and its precise workings continue to challenge our grasp of how the universe structures itself. Now, let's turn our attention from the grand architecture of the cluster to the very air it breathes, the superheated plasma that fills the space between galaxies, known as the intracluster medium. We've already seen how this gas glows in X-rays and how its immense heat is a mystery in itself, but there's another layer to this enigma hidden within its chemical fingerprint. When astronomers use powerful spectrometers to break down the X-ray light from this plasma into its constituent colors, they don't see a simple, pristine composition of hydrogen and helium, the primordial elements forged in the Big Bang. Instead, they see the clear, unmistakable signatures of heavier elements: iron, oxygen, silicon, neon, and magnesium. This is the phenomenon of chemical enrichment, and it tells us that the space between galaxies is littered with the ashes of countless dead stars. The very fact that this intergalactic space is polluted with these metals is profound. It means that the elements that make up our planets and our very bodies have been blown out of their home galaxies and scattered across the cosmos on an unimaginable scale. The central mystery, however, isn't just that these elements are present, but that they appear in specific and sometimes baffling ratios. Think of it as cosmic forensics. Each type of stellar explosion leaves behind a distinct chemical signature. There are two primary kinds of supernova responsible for forging these heavy elements. Core collapse supernova come from the rapid death of short-lived massive stars. These explosions are prolific producers of what astronomers call alpha elements: oxygen, neon, magnesium, and silicon. They are the universe's primary oxygen factories. On the other hand, type Ia supernova, which occur when a white dwarf star is triggered to explode, are tremendous producers of iron and nickel. They are the universe's iron furnaces. By measuring the ratio of iron to oxygen in the intracluster medium, scientists can essentially count the number of each type of supernova that has ever occurred throughout the entire history of the cluster, providing an integrated record of its stellar life and death. This is where the observations in the Coma Cluster present a fascinating puzzle. The chemical mix we find in its hot gas doesn't always align neatly with the predictions from our models of galactic chemical evolution. The ratio of iron to silicon, for instance, or the relative amounts of different alpha elements, can show surprising variations from one part of the cluster to another. In some regions, the balance of elements suggests a history dominated by a steady, prolonged drizzle of type Ia supernova, the kind that take billions of years to occur. In other areas, the chemical fingerprint looks more like the aftermath of a sudden, intense burst of core collapse supernova from a rapid wave of star formation in the distant past. The gas isn't a uniformly mixed soup. It's a patchwork of different enrichment histories, each patch telling a different story about the cluster's violent past. One of the most significant head-scratchers involves the overall abundance of iron. The amount of iron floating in the Coma Cluster's intracluster medium is staggering, literally millions of times the mass of our entire Sun, all in the form of iron atoms dispersed through the hot plasma. To produce this much iron requires an incredible number of type Ia supernova. But when astronomers run simulations that model the formation and evolution of a cluster like Coma, they often find it difficult to reproduce this level of iron enrichment. The models tend to underproduce the iron we actually observe. This iron excess problem suggests that our understanding of how and when type Ia supernova explode may be incomplete. Perhaps they are more efficient at producing iron than we thought, or maybe they were far more common in the early universe during the cluster's formative years than our current stellar population models allow. Alternatively, the process of ejecting this iron from galaxies into the intergalactic void might be more effective than we've calculated, with galactic winds and AGN-driven outflows acting as powerful conveyor belts, tirelessly dumping the processed remains of stars into the cluster's atmosphere. Another perplexing detail comes from the pattern of the alpha elements. The relative proportions of oxygen, neon, and magnesium to silicon can act as a cosmic clock. Core collapse supernova from massive stars explode very quickly after a burst of star formation within a few million years. Type Ia supernova, however, have a long and delayed fuse. They can take hundreds of millions or even billions of years to detonate. This means the chemical enrichment from these two sources is staggered in time. The specific alpha element ratios we see in Coma's gas suggest a complex and multi-stage enrichment history. It appears that a significant portion of the enrichment happened very early when the cluster was first assembling, in a frenzy of star formation and core collapse supernova. But then, there was a later, prolonged phase where type Ia supernova continued to pepper the intracluster medium with iron, slowly changing the chemical balance over billions of years. The puzzle is that this late-time enrichment seems almost too efficient. leaving a chemical imprint that is difficult to replicate in our most sophisticated simulations of cluster formation. The uneven distribution of these elements adds yet another layer of intrigue. The chemical makeup isn't uniform, it's stratified. Generally, the concentration of iron and other heavy elements is higher near the cluster's core and decreases as you move outward. This makes a certain intuitive sense. The core is where most of the galaxies, and therefore most of the supernova, have always been concentrated. However, there are also large, coherent regions where the chemical composition is distinctly different from its surroundings. These patches are like isolated chemical islands, preserving the unique enrichment history of a specific group of galaxies that merged into the cluster long ago. Finding a pocket of gas that is exceptionally rich in oxygen, for example, could be the ghostly remnant of a past galaxy group that was dominated by intense, short-lived starbursts, whose core collapse supernova polluted their local environment before the group was ever absorbed into the larger Coma system. This patchiness tells us that the intracluster medium has not been completely homogenized. It still holds the fossilized memories of the individual building blocks that came together to form the colossal cluster we see today. Ultimately, the strange chemical enrichment of the Coma Cluster's intracluster medium is a deep-time mystery. It is the integrated output of trillions of stars over billions of years, a story written in a language of elemental ratios that we are still learning to read. Every discrepancy between observation and theory, every unexpected abundance of iron or peculiar ratio of oxygen to silicon is a clue pointing to a gap in our understanding. It forces us to reconsider the life cycles of stars, the efficiency of supernova, and the powerful galactic winds that must have swept these newly forged elements out of their birthplaces and into the intergalactic wilderness. The hot gas between the galaxies, far from being a simple backdrop, is a rich chemical archive, and its unexplained composition ensures that the history of star formation and death in the Coma Cluster is a story still being written. Amidst the swirling galaxies and the searing heat of the intracluster gas lies an invisible, yet immensely powerful, force field shaping the very fabric of the cluster. This is the Coma Cluster's magnetic field, a complex and pervasive web of energy that weaves through the spaces between galaxies, a silent, structuring presence we can only detect through its subtle influence on light and particles. We know it's there because of two key observational clues. The first, as we saw with the giant radio halo, is the presence of synchrotron radiation, that faint, diffuse radio glow that tells us ultra-high-energy electrons are spiraling around magnetic field lines. The second, even more precise method is a phenomenon known as Faraday rotation. When polarized radio waves from a distant quasar or galaxy pass through a magnetized plasma, like the intracluster medium, the magnetic field actually twists the orientation of those radio waves. By measuring this subtle rotation, astronomers can not only confirm the field's existence, but also map its strength and direction along our line of sight. The results from these techniques are startling. The magnetic field in the Coma Cluster is not a weak, insignificant thing. It is surprisingly strong, with a strength measured in microgauss, which might sound small, but remember, this field is coherent across millions of light years. To generate a magnetic field that's strong across such a colossal volume requires a source of immense and sustained power. And the origin of this cosmic electromagnet is a mystery that strikes at the heart of how the universe builds its largest structures. One of the great debates surrounding this magnetic field centers on its ultimate genesis. Did it grow from tiny, primordial seeds, or was it forged in the violent hearts of galaxies and then spread throughout the cluster? The primordial origin theory is a story of cosmic amplification. It proposes that in the very early universe, weak magnetic fields were generated by processes in the infant cosmos, perhaps by the motion of plasma in the first stars and galaxies. These seed fields would have been incredibly faint, trillions of times weaker than the field of a common refrigerator magnet. As the protocluster that would become Coma began to collapse and form, this plasma was stirred, compressed, and stretched by the immense gravitational forces and turbulent motions of the assembling cluster. This turbulent dynamo effect, acting over billions of years, could have amplified those weak seed fields into the robust microgauss strength field we observe today. It's a compelling top-down picture where the large-scale structure of the cluster itself acts as the engine that builds its own magnetic infrastructure from the ground up. The alternative, a bottom-up scenario, suggests the field was built piece by piece, injected into the intergalactic void by the frantic activity of the cluster's residents. Every galaxy that has ever lived within Coma has contributed to this potential pollution. Stellar winds from massive stars and the vast, expanding shells of supernova remnants are filled with hot, magnetized plasma. As these winds blow out of their host galaxies, they can carry snatches of the galaxy's magnetic field with them, seeding the intracluster medium with pockets of magnetism. An even more potent delivery mechanism comes from the active galactic nuclei we've discussed. The colossal jets from supermassive black holes don't just inflate X-ray cavities, they are also fire hoses of magnetized plasma, directly injecting ordered magnetic fields and energetic particles into the cluster's heart over vast distances. In this view, the cluster-wide magnetic field is the accumulated exhaust, the collective magnetic pollution from trillions of stellar deaths and countless Aegean outbursts, all stirred together by the cluster's dynamics. The truth likely involves a combination of both processes, but untangling their relative contributions is a monumental task. The field structure, whether it is smooth and ordered or chaotic and tangled, holds the key, as each origin story would leave a different imprint on the magnetic architecture we observe today. Beyond the question of its origin, the cluster's magnetic field plays a surprisingly active and multifaceted role in the ecosystem, acting as both a cage and a sculptor. Its most clear-cut job is confining the sea of cosmic rays, those high-energy protons and electrons that fill the cluster. Without a magnetic field, these particles would simply fly off in straight lines at nearly the speed of light and quickly escape into intergalactic space. But the field's invisible lines act as a labyrinth, forcing the charged particles to spiral endlessly along them, trapping them within the cluster's gravitational well for far longer than would otherwise be possible. This confinement is absolutely essential for the existence of the giant radio halo. It's the magnetic field that keeps the high-energy electrons in place long enough to produce the synchrotron radiation we detect. In this sense, the magnetic field is the unseen prison warden for the cluster's most energetic inhabitants. But the field's influence extends deep into the realm of gas dynamics, where its effects are more subtle and complex. This tenuous magnetized plasma is a state of matter known as a magnetofluid, where magnetic pressure and gas pressure vie for dominance. In some regions, the magnetic field can provide crucial additional support against gravitational collapse, helping to stabilize vast clouds of gas and preventing them from falling too quickly into the cluster core. It can also suppress certain instabilities and regulate the mixing of different gas phases. However, the field can also be a source of structure itself. It can channel the flow of hot plasma, guide the propagation of shock waves from galactic collisions, and even influence the formation and evolution of the very filaments we see in X-rays. The magnetic field introduces a layer of complexity to the fluid dynamics of the cluster that our simulations are still struggling to capture accurately. Its presence means that the intracluster medium is not a simple, ideal gas. It is a sophisticated, magnetized atmosphere where invisible lines of force work in concert with gravity and pressure to shape the destiny of the ordinary matter that makes up the cluster's visible breath. This pervasive, powerful, and enigmatic magnetic field is a fundamental, yet still poorly understood, character in the story of the Coma Cluster, a hidden force whose origins and full influence we are only just beginning to unravel. Deep within the swirling heart of the Coma Cluster, a place we have come to know as a galactic graveyard where spirals are shredded and transformed, there exists a breathtaking anomaly. It's a celestial survivor that defies the grim fate of its neighbors, the magnificent spiral galaxy NGC 4911. To gaze upon it is to witness a cosmic contradiction. Here, in one of the most violent and disruptive environments in the known universe, a galaxy has managed to hold onto its elegant pinwheel structure. Its graceful spiral arms, delicately laced with pink star-forming regions and dark lanes of dust, spiral outward from a bright core. Looking for all the world like it should be floating in the peaceful isolation of intergalactic space, not trapped in the chaotic core of a massive cluster. The very existence of NGC 4911 presents a profound and beautiful mystery. In a realm dedicated to destruction, how has this one galaxy managed to preserve its delicate architecture? The survival of a classic spiral structure here is nothing short of remarkable. We have already explored how the Coma Cluster systematically dismantles spiral galaxies through a brutal combination of ram pressure stripping, galaxy harassment, and strangulation. These processes tear out a galaxy's gas, disrupt its orderly rotation, and gravitationally pummel it into a bland, elliptical shape. The fact that NGC 4911 has withstood this onslaught while maintaining its spiral identity suggests it possesses a unique set of defenses or has been incredibly fortunate in its cosmic journey. Astronomers are actively investigating several compelling theories to explain its resilience, and each possibility reveals a different facet of how a galaxy can endure in a hostile world. One prominent theory suggests that NGC 4911 might be a relatively new arrival to the inner turmoil of the cluster core. Imagine a galaxy falling into the cluster from the outskirts, from the quieter cosmic suburbs. It's possible that NGC 4911 is on its first or second infall, a recent immigrant that has not yet experienced the full, cumulative brutality of the cluster environment. It may still be in the early stages of its interaction, allowing it to retain much of its original gas and structure. In this scenario, we are catching it at a special moment in time, a fleeting snapshot of a spiral galaxy just beginning its fight for survival. Its current state is not necessarily permanent. It could be in a transitional phase, and in another few 100 million years, it may finally succumb to the pressures and begin its own transformation into a red and dead elliptical. This recent infall idea turns NGC 4911 into a living clock, helping astronomers gauge the timescales over which the cluster's destructive forces operate. A second, closely related theory focuses on the specific path the galaxy takes through the cluster, its orbital dynamics. Not all orbits are created equal. A galaxy on a highly radial orbit, one that plunges directly through the densest central region of the cluster, will experience the most extreme ram pressure and gravitational tides. It's a suicide dive. However, NGC 4911 might be on a much more fortunate path, a wider, more circular orbit that keeps it at a safer distance from the very epicenter of the violence. Think of it as skating around the edge of a storm rather than driving through its eye. This fortunate trajectory would subject the galaxy to a less intense and less frequent barrage from its neighbors and the intracluster medium, giving it precious time to recover between disruptive encounters. This orbital fortune could provide the breathing room needed for the galaxy to maintain its internal structure and continue forming stars, effectively allowing it to hide in plain sight within the chaotic cluster. Yet another fascinating possibility lies within the galaxy's own internal architecture. Perhaps NGC 4911 is simply built tougher than most spirals. It possesses an unusually bright and massive central bulge, a dense spherical concentration of stars at its core. This high-density core could act as a powerful gravitational anchor, stabilizing the entire disk against the external forces trying to tear it apart. When gravitational tides from a passing galaxy try to warp the disk or stir up its stars, This dense central mass provides a restoring force, like a heavy keel on a sailboat that keeps it upright in rough seas. Furthermore, the galaxy appears to be a barred spiral with a straight bar of stars cutting through its center. This bar structure can also contribute to stability by funneling gas and driving internal motions that help the galaxy maintain its equilibrium against external shocks. In this view, NGC 4911 isn't just lucky. It's inherently robust, its own dense core serving as a fortress against the environmental pressures that have overwhelmed other, less fortified spirals. But the mystery deepens when we look even closer. Recent high-resolution observations reveal that the survival of NGC 4911 is not a complete one. It is a galaxy under active assault. While its grand design spiral structure remains stunningly intact, there are clear signs that the cluster is beginning to take its toll. The galaxy's outer disk shows subtle evidence of distortion, and its star formation rate, while still significant, may not be as high as that of similar spirals in the field. This suggests we are not looking at an invincible galaxy, but rather one in a state of delicate balance. The destructive forces of the cluster and the galaxy's own internal resilience are locked in a tug of war, and for now, the galaxy is holding its own. This makes it an invaluable natural laboratory. By studying the precise points where it shows stress, the specific regions where gas is being stripped or star formation is being quenched, astronomers can calibrate the strength of the environmental forces at play with unprecedented precision. Ultimately, the ghostly persistence of NGC 4911's spiral structure is more than just a cosmic curiosity. It is a critical test case for our understanding of galaxy evolution. Its survival challenges the simplistic narrative that all galaxies in dense clusters must be rapidly and efficiently transformed. It demonstrates that the outcome for any individual galaxy depends on a complex interplay of factors: its entry time into the cluster, its specific orbital path, and its own internal strength. NGC 4911 stands as a magnificent exception that proves the rule is more nuanced than we thought. A beautiful reminder that even in the harshest of environments, nature can find a way to preserve its most elegant forms, if only for a little while longer. But even as we account for the immense quantities of dark matter and the brilliant, searing glow of the hot gas, a quieter, more fundamental problem persists in the shadows of the Coma Cluster, a problem that challenges our most basic inventory of the cosmos. This is the missing baryon problem, and while it may sound like an obscure accounting error, it strikes at the very heart of our understanding of what the universe is made of. Baryons are the particles that make up all the familiar matter we see around us, the protons and neutrons that form stars, planets, and us. According to the precise measurements of the cosmic microwave background, the afterglow of the Big Bang, we know with great certainty what fraction of the universe's total mass energy should be in the form of these baryons. It's a cosmic recipe, and we know how much of the normal ingredient should be in the mix. Yet, when we perform a detailed census of a colossal structure like the Coma Cluster, adding up all the baryons we can see in the form of stars and the hot, X-ray emitting intracluster gas, we come up short. A significant portion of the universe's normal matter is simply not where we expect it to be. The cluster, for all its thousands of galaxies and vast atmosphere of plasma, is still missing a chunk of its allotted normal matter. This isn't a small discrepancy. The numbers suggest that within the confines of the Coma Cluster, we might only be detecting somewhere between 1/2 and 2/3 of the baryonic matter that our cosmological models insist must be there. So, where did it go? The answer likely lies not in the brilliant, easy-to-see components, but in a far more elusive and difficult-to-detect phase of matter known as the warm-hot intergalactic medium, or WIM. Imagine a gaseous web that spans the entire universe, a network of filaments connecting galaxy clusters like Coma to the rest of the cosmic large-scale structure. The gas in this web isn't cold and dense, nor is it searingly hot like the plasma at the heart of a cluster. it exists in a lukewarm, in-between state, with temperatures ranging from 100,000 to 10 million degrees Celsius. At these temperatures, the gas doesn't emit the kind of bright, focused X-rays that our telescopes readily pick up from the cluster core. Instead, it emits a faint, diffuse glow that is incredibly challenging to distinguish from the background, and it primarily absorbs light in very specific, hard-to-observe wavelengths from distant, bright objects like quasars. It's the universe's hidden, tepid ocean, and the missing baryons from the Coma Cluster are almost certainly suspended within it, woven into the vast cosmic web just beyond the cluster's immediate gravitational grasp. Finding this missing matter is a bit like trying to map a complex, invisible network of pipes by only watching the steam that occasionally leaks out. Astronomers use incredibly bright, distant lighthouses known as quasars. As the light from a quasar travels across billions of light years to reach us, it passes through these filaments of warm, hot gas. The specific atoms in the WIM, things like highly ionized oxygen, neon, and carbon imprint faint absorption lines onto the quasar's spectrum like a chemical barcode. By analyzing these subtle fingerprints, we can confirm the presence and composition of the gas. The challenge is that these absorption lines are exceedingly weak, and to build up a statistical picture of the WIM, we need to observe the spectra of many quasars whose lines of sight pass near massive clusters like Coma. It is a painstaking, indirect method of detection, but it remains our best hope for completing the cosmic ledger and finding the universe's lost atoms. The implications of solving this puzzle extend far beyond the Coma Cluster itself. The missing baryon problem is universal. It applies to the cosmos as a whole. If we can successfully account for the baryons in a massive, nearby cluster like Coma, it would validate our entire model of cosmic structure formation. It would confirm that the cosmic web we simulate in our computers is real, and that it contains the bulk of the normal matter in the universe hiding in plain sight. Furthermore, understanding the distribution and state of these baryons is crucial for tracing the flow of material into and out of clusters. The WIM is not a static reservoir, it is the primary source of fuel for future galaxy growth. Gas from these filaments continuously drains into the cluster's gravitational well, feeding the intracluster medium and potentially providing new material for star formation, albeit at a trickle. At the same time, powerful galactic winds and Aegean outflows can pump enriched material from inside the cluster back out into the web, creating a vast cosmic-scale circulation system. The missing baryons are not truly lost. They are part of this great, slow-moving cycle, and finding them completes our picture of how matter, the very stuff of stars and planets, is distributed and recycled on the largest scales imaginable. As we've journeyed through the violent transformations and ghostly remnants of the Coma Cluster, we've largely explored its internal dynamics, the clashes and transformations happening within its bounds. But to complete our investigation, we must now pull back to the widest possible perspective, to see the cluster not as an isolated island, but as an integral part of the universe's largest and most fundamental structure. This brings us to our final and perhaps most grand, unexplained phenomenon, the large-scale alignment of the cluster and its galaxies with the cosmic web. The idea is both simple and staggering. The orientations of the galaxies themselves, the way they spin and point, may not be random accidents of nature. Instead, their positions and spins appear to be subtly correlated with, and perhaps even dictated by, the invisible architecture of the dark matter filaments that form the skeleton of the cosmos. To visualize this, imagine the universe on its very largest scales not as a random scattering of galaxies, but as a magnificent three-dimensional spiderweb. This is the cosmic web, a network of immense filaments of dark matter and gas that stretch across billions of light years, connecting dense clusters like Coma at their intersections. Between these filaments lie the vast, empty cosmic voids, regions of startling emptiness, For decades, our most sophisticated computer simulations of the universe's evolution have predicted that this web should not be passive. It should exert a guiding hand on the galaxies that form within it. As gas flows from the voids into the filaments and then drains along those filaments toward the hungry clusters at the nodes, it is thought that this orderly flow of material can impart a preferred direction of spin to the galaxies that condense from it. A galaxy forming within a filament might be expected to spin in a plane that aligns with that filament, like a leaf caught in a river current. The cluster as a whole, sitting at the crossroads of several such filaments, should itself reflect this grand design in the arrangement of its thousands of members. The profound mystery is that in the Coma Cluster we are beginning to find tantalizing yet controversial observational evidence that this prediction is real. When astronomers meticulously map the positions and orientations of the thousands of elliptical galaxies within Coma, they don't always find a perfectly random distribution. Instead, they detect faint statistical hints of alignment. Certain populations of galaxies, particularly those that are brighter and more massive, show a tendency for their long axes, their shapes to point in similar directions, and these directions seem to coincide with the axes of the large-scale filaments that we believe feed into the cluster. It's as if the ghosts of the ancient rivers that built the cluster are still visible in the frozen poses of its galactic inhabitants. Even more astonishingly, studies of the few surviving spiral galaxies in the cluster's outskirts have looked at the direction of their spin axes. The initial and still hotly debated results suggest that these rotation axes are also not entirely random. They too may show a preference for being perpendicular to the direction of the nearest major filament. This would mean that the galaxy's disk is spinning in alignment with the flow of the cosmic web, a fossilized record of the orderly currents that gave it birth billions of years ago. Confirming this phenomenon is one of the most difficult challenges in modern cosmology. The statistical signal is incredibly weak and easily drowned out by the later, violent history of the cluster itself. The chaotic gravitational interactions between galaxies, the very harassment and mergers we've discussed should, in theory, have randomized these primordial alignments over time, scrambling any memory of their initial formation. The fact that we might still be able to detect a correlation today is deeply puzzling. It suggests that the imprint of the cosmic web is far more resilient than we thought, or that the alignments we see are not solely primordial. Perhaps the continuous, ongoing accretion of new galaxies along the cosmic filaments is constantly refreshing this pattern, imprinting a preferred direction on the cluster even as it matures. The alignments we detect, then, would not be a static fossil, but a living signature of the cluster's continued growth, a real-time testament to the fact that the Coma Cluster is still being woven into the cosmic tapestry at this very moment. If these alignments are indeed real, they force us to confront a critical gap in our understanding of galaxy formation. Our current models struggle to reproduce the precise strength and scale of these observed correlations. The physics of how angular momentum is transferred from the swirling, expanding universe down to the scale of individual galaxies, a process known as tidal torque theory, is notoriously complex. It involves the subtle gravitational interactions between a proto-galaxy and all the surrounding matter in its cosmic neighborhood. While the basic principle is sound, the devil is in the details. The specific alignments we see in Coma suggest that the surrounding dark matter environment exerts a more powerful and coherent influence than our simulations typically account for. This could mean that dark matter halos are more strongly connected to their cosmic web environment than we've modeled, or that the gas physics involved in galaxy formation plays a more active role in preserving this spin memory. Unraveling this mystery is not just about understanding galaxy orientations. It's a fundamental test of our entire picture of how cosmic structure, from the largest filaments down to individual galaxies, emerges from the smooth soup of the Big Bang. Ultimately, the potential alignment of the Coma Cluster with the cosmic web brings our journey full circle. It connects the most intimate stellar transformations we've witnessed to the most immense architecture of the universe. This grand pattern suggests that the fate of a galaxy is written not only by its local environment, the violent cluster core, but also by its cosmic address within the great dark matter highways of the cosmos. From the missing dark matter in a single giant galaxy to the coordinated spin of thousands of galaxies across millions of light years, the Coma Cluster presents a layered, interconnected set of mysteries. Each one, from the smallest to the largest scale, challenges our understanding and pushes the boundaries of our knowledge, reminding us that the universe is a place of both beautiful order and profound, unanswered questions. As we unravel the enigmas hidden within the galaxies of the Coma Cluster, we must remember that this cosmic metropolis is far more than just a collection of individual curiosities. It serves as a fundamental benchmark, a fixed point in the expanding universe that allows us to measure the cosmos itself. This brings us to one of the most pressing issues in all of modern cosmology, a problem where the Coma Cluster plays a starring role: the Hubble tension. At its heart, this is a crisis surrounding a single, crucial number, the Hubble constant, which represents the current expansion rate of our universe. For decades, astronomers have pursued two primary, independent methods to pin down this value, confident they would converge on a single, universal truth. Instead, they have found a stubborn and growing discrepancy that threatens to reveal a fundamental flaw in our understanding of physics. One method looks at the local, modern universe. It uses a series of carefully calibrated distance markers, a cosmic distance ladder, to measure how fast galaxies relatively close to us are receding. The first rung of this ladder involves incredibly precise distance measurements to objects within our own galaxy. The next crucial rung often relies on a specific class of pulsating stars known as Cepheid variables, whose predictable brightness variations allow us to gauge their distance with remarkable accuracy. By observing these Cepheids in nearby galaxies, we can calibrate even brighter standard candles like Type Ia supernova, whose immense and consistent peak brightness allows them to be seen across vast cosmic distances. When we combine all these measurements, we arrive at a value for the Hubble constant that describes the universe's expansion today. This local measurement is exceptionally precise, but it yields a number that is consistently and significantly higher than the value derived from the other, completely different approach. This second method looks back to the very dawn of time, to the infant universe as revealed by the cosmic microwave background, the faint afterglow of the Big Bang. Exquisitely detailed maps from missions like Planck show the subtle variations in this ancient light, which act as a frozen snapshot of the universe when it was only 380,000 years old. Using our well-established model of cosmic evolution, which incorporates dark energy, dark matter, and the laws of physics as we know them, we can run the clock forward from that early state to predict what the expansion rate should be today. This prediction provides a value for the Hubble constant that is based on the physics of the primordial universe. The problem, the core of the tension, is that this early universe prediction is consistently lower than the value we measure directly in our local neighborhood. The two most trusted ways of measuring the universe's expansion are in clear, unresolved disagreement. It's as if you used two different, highly accurate watches to time the same event, and one consistently told you it took 5 minutes while the other insisted it was only 4. This isn't a small observational error, it's a discrepancy that persists even as our measurements become more and more precise, suggesting that we might be missing a crucial piece of physics in our standard model of cosmology. This is where the colossal and stable structure of the Coma Cluster becomes a critical arbiter in the debate. To build a reliable cosmic distance ladder, you need firm foundational rungs. The Coma Cluster is one of the most important of these rungs because of its immense distance and its role as a massive, gravitationally bound system. It provides a unique and stable platform for testing and refining our distance measurements. The key is to measure the distance to the Coma Cluster with near absolute certainty, completely independent of the contentious methods that rely on Cepheids or the cosmic microwave background. If we can establish a direct, rock-solid distance to Coma, it can act as a calibration point that either reinforces the local measurement method or casts doubt upon it, thereby influencing which side of the Hubble tension carries more weight. One of the most promising techniques for achieving this is surface brightness fluctuations. This method exploits the pixelated nature of distant galaxies in high-resolution images. In a nearby galaxy, a telescope can resolve millions of individual stars, but in a galaxy in the Coma Cluster, the stars blur together into a smooth glow. However, there is still a subtle graininess to that glow, caused by the fact that a few of the very brightest giant stars are still detectable as individual points of light within each pixel of the detector. By analyzing this statistical fluctuation in pixel brightness from one part of the galaxy to another, astronomers can derive the galaxy's distance. The farther away the galaxy, the smoother and less grainy its surface brightness appears because more stars are blended into each pixel. This powerful technique, when applied to the many elliptical galaxies in Coma, can provide a direct geometric distance that sidesteps many of the assumptions and potential pitfalls of the traditional distance ladder. New and upcoming observations of the Coma Cluster, particularly with powerful instruments like the James Webb Space Telescope and the next generation of extremely large ground-based telescopes, are poised to revolutionize this effort. Their unprecedented resolution and sensitivity will allow for surface brightness fluctuation measurements of unparalleled precision. They will also enable other direct methods, such as the tip of the red giant branch approach. This technique identifies the point at which the oldest and most luminous red giant stars in a galaxy suddenly ignite a shell of helium around their cores, causing a predictable and recognizable peak in their brightness. By pinpointing this specific brightness level in the crowded stellar populations of Coma's galaxies, we can obtain another robust direct distance measurement. When multiple independent methods like these all converge on the same distance for the Coma Cluster, it gives us a bedrock level of confidence in that number. A firmly established distance to the Coma Cluster would have profound implications for the Hubble tension. If the direct distance to Coma confirms the calibrations used by the local measurement team, it would lend powerful support to the higher value of the Hubble constant. This would force cosmologists to seriously consider that our standard model of the universe is incomplete. We might need to incorporate new, exotic physics to explain the discrepancy. Perhaps dark energy, the mysterious force driving cosmic acceleration, is not constant but evolves over time, becoming stronger in the recent universe. Or maybe there exists a new, previously unknown type of relativistic particle that zipped through the early cosmos, subtly altering the conditions captured in the cosmic microwave background. Some theories even suggest modifications to the fundamental force of gravity itself on the largest scales. A confirmation of the higher expansion rate would open the door to these revolutionary possibilities. Conversely, if the new, direct measurements of the Coma Cluster's distance were to instead reveal an error in the local distance ladder calibration, it could resolve the tension in favor of the early universe prediction from the cosmic microwave background. This would mean our standard cosmological model is essentially correct, and the discrepancy was due to a subtle, cumulative error in our measurement of distances to nearby galaxies. While this might be a less revolutionary outcome, it would still be a monumental achievement, solidifying our understanding of the universe's composition and history. It would affirm that the model built from the afterglow of the Big Bang accurately describes the cosmos from its first moments to the present day. The Coma Cluster, a vast city of galaxies, thus finds itself at the center of a debate that reaches across nearly 14 billion years of cosmic history, its measured distance holding the key to determining whether our universe operates by the rules we have written, or if we must tear up the textbook and start anew. But this grand tour of mysteries is not the end of the story. It is merely the prelude to a new era of discovery. The unresolved questions hanging over the Coma Cluster have not gone unnoticed by the global astronomical community, and a new generation of observatories, both in space and on the ground, is now being tuned to focus on this cosmic metropolis with an acuity that was pure science fiction just a generation ago. These are not merely incremental upgrades, they are revolutionary instruments designed to peer into the heart of these enigmas, and they promise to transform our understanding of the cluster in ways we can only begin to imagine. The hunt for answers is accelerating, and the tools for the job are nothing short of breathtaking. Leading this charge is the James Webb Space Telescope, an instrument that has already begun to rewrite the textbooks on the early universe. For the Coma Cluster, Webb's incredible infrared sensitivity and resolution are a game-changer for studying its stellar populations. While previous telescopes saw the cluster's galaxies as largely red and dead, Webb can dissect their faintest light, picking out the subtle, specific signatures of truly ancient stars and distinguishing them from any residual, hidden pockets of younger stars. It can peer through the veils of dust that might obscure ongoing, low-level star formation, finally giving us a definitive census of whether the dead galaxies are truly finished with stellar creation. Furthermore, Webb's powerful spectrographs can analyze the chemical composition of intracluster stars and the faint tidal streams around galaxies like NGC 4911 with unprecedented detail, allowing us to trace the origin of these exiled stars back to their parent galaxies and reconstruct the cluster's merger history with the precision of a cosmic archaeologist. On the ground, the upcoming Vera C. Rubin Observatory is set to conduct a relentless, decade-long cinematic survey of the entire southern sky. Its sheer scale of data collection will be transformative for studying the Coma Cluster's dynamics. Whereas we currently have snapshots of galaxy motions, Rubin will provide a high-definition movie. By imaging the cluster repeatedly over its operational life, it will track the subtle, proper motions of thousands of individual galaxies within Coma, mapping their complex orbits with a clarity never before possible. This will allow us to directly test the anisotropic velocity distribution, confirming the patterns that suggest a recent major merger and perhaps even identifying specific streams of galaxies that still remember their infall from a particular cosmic filament. Rubin's deep, wide-field vision will also be unparalleled for finding the faintest members of the cluster, countless new ultra-diffuse galaxies like Dragonfly 44, and perhaps even the first convincing, isolated dark galaxy candidates by spotting their gravitational influence on the faint glow of the intracluster light. Looking further into the future, the European Space Agency's Athena mission, the Advanced Telescope for High-Energy Astrophysics, is designed to be the ultimate X-ray observatory. Its mission is to directly confront the cooling flow crisis and the feedback enigma. Athena will map the hot intracluster medium of the Coma Cluster with a spectral and spatial resolution that makes current X-ray telescopes seem blurry and crude. It will be able to trace the motions of the superheated gas in stunning detail, watching as it is churned by the rising X-ray cavities and the shock fronts from Aegean outbursts. For the first time, we will be able to directly measure the energy transfer from these cavities into the surrounding plasma, quantifying the sound waves and turbulence that provide the heating, and finally closing the book on the energy accounting problem. Athena's sensitive spectrometers will also create exquisitely detailed chemical maps of the intracluster medium, resolving the puzzling patches of different elemental abundances and tracing them back to their galactic sources, effectively allowing us to write the definitive history of star formation and death for the entire cluster. The combined power of these observatories opens the door to discoveries that today sound like fantasy. One of the most profound goals is the potential to indirectly image the dark matter filamentary web itself. While we cannot see dark matter directly, its gravitational presence dictates the flow of hot gas. Athena's ultra-sensitive X-ray observations, combined with gravitational lensing maps from Rubin and spectroscopic data from Webb, could allow us to create a three-dimensional map of the gas dynamics with such precision that the underlying dark matter skeleton becomes unmistakably clear. We would no longer be inferring its structure, we would be tracing its outline through the behavior of the matter it controls. This could finally allow us to test whether the anomalous lensing signals we see are indeed caused by dense dark matter subhalos or by something even more exotic like cosmic strings. These new eyes on the cosmos will also let us witness galaxy transformation in a form of real-time cosmic observation. With the Rubin Observatory's time-lapse view of the sky, we may actually catch a spiral galaxy in the precise moment it begins to be stripped by ram pressure, watching as its gas is torn away and its star formation is abruptly quenched over a period of years, not eons. We could observe the gravitational interactions that lead to high-velocity ejections, tracking the paths of galaxies before and after a close encounter with a giant elliptical. This moves our understanding from reconstructing history from fossils to observing the evolutionary process as it happens, providing direct dynamic evidence for the theories we have built from static snapshots. Yet, for every mystery these new tools are poised to solve, they are guaranteed to unveil new, deeper puzzles that we cannot yet even formulate. The history of astronomy teaches us that every time we look at the universe in a new way, we are humbled by the complexity we uncover. As we probe the magnetic fields of the intracluster medium with greater sensitivity, we may find their structure is even more ordered and powerful than expected, suggesting an origin we haven't contemplated. As we discover thousands more ultra-diffuse galaxies, we may find some that defy the categories of either dark matter-dominated or tidal origin, pointing to entirely new pathways of galactic evolution. The precise measurement of the Hubble constant using the Coma Cluster as a calibrator may not cleanly resolve the tension, but instead deepen it, forcing us to accept that our standard model of cosmology requires a more radical overhaul than anyone has yet proposed. The Coma Cluster has guarded its secrets for hundreds of millions of years, and while we are now building the keys to its deepest vaults, the greatest revelation may be that the universe's largest structures are even more strange, more dynamic, and more wonderfully mysterious than we have ever dared to dream. From the ghostly giant with missing dark matter to the ethereal wisp overflowing with it, from the colossal radio halo powered by an unseen engine to the ancient, silent filaments that defy disruption, our journey through 25 of the Coma Cluster's greatest mysteries paints a portrait of a universe that is far more dynamic, complex, and stranger than we ever imagined. We have wandered through a galactic graveyard of red and dead stars, only to find brilliant stellar explosions and the delicate, surviving spiral of NGC 4911. We have witnessed galaxies being flung out at incredible speeds and others being whittled down to their dense cores, revealing impossibly massive black holes. We have pondered dark galaxy candidates and gravitational anomalies, studied the tragic beauty of jellyfish galaxies and the colossal feedback of black holes that heat the cosmos. We have tracked the chemical enrichment of intergalactic space and mapped its pervasive magnetic field, all while confronting the fundamental accounting problem of the universe's missing matter. And we have seen hints that the entire cluster, in its vastness, may be aligned with the invisible cosmic web, a fossilized imprint of the universe's largest structure. Each phenomenon, from the scale of a single star to the motion of thousands of galaxies, is a piece of a single grand puzzle. What becomes overwhelmingly clear is that the Coma Cluster is so much more than a simple collection of galaxies. It is a supreme cosmic laboratory. Its immense scale, violent history, and rich complexity provide a unique natural experiment for testing the laws of physics under conditions we could never hope to replicate on Earth. The anomalies we observe here are not mere curiosities. They are severe stress tests for our most fundamental theories. The missing dark matter in its giants and the overabundance in its dwarfs challenge the very nature of this mysterious substance. The precise balance that prevents a catastrophic cooling flow probes our understanding of energy and thermodynamics on a million light-year scale. The coordinated motion of its galaxies questions our assumptions about cosmic equilibrium and assembly. Every unexplained observation is a potential crack in the foundation of the standard model of cosmology, a hint that a deeper, more complete theory of the universe is waiting to be discovered. Ultimately, to understand the Coma Cluster is to take a significant step toward understanding the cosmos itself. The processes at work here, gravity, magnetism, particle acceleration, and stellar evolution, are the same processes that govern the entire universe. By studying them in this extreme environment, we see them writ large, their effects amplified, and their interactions laid bare. The cluster acts as a cosmic magnifying glass, revealing the subtle interplay between dark and light, between creation and destruction that shapes all of cosmic history. The answers we seek in this distant metropolis are not just about one cluster of galaxies. They are about the fundamental rules that orchestrate reality, from the smallest subatomic particles to the vast, expanding fabric of space-time. As our tools, the James Webb Space Telescope, the Vera-C, Rubin Observatory, the Athena mission, and others, turn their powerful gaze toward this region, we stand on the brink of revelations that will undoubtedly reshape our cosmic perspective. The next decade promises to transform these 25 mysteries from unanswered questions into the foundations of a new understanding. But this journey of discovery is not just for astronomers and physicists. It belongs to all of us, to anyone who has ever looked up at the night sky with a sense of wonder. So the next time you find yourself under a clear, dark sky, take a moment to look toward the constellation Coma Berenices. Know that in that faint patch of darkness, visible with only a small telescope, lies a universe of enigmas, a city of galaxies where the very laws of nature are being probed and questioned. Stay curious, follow the discoveries as they unfold, and remember that we are all part of a species brave enough to look deep into the cosmos and humble enough to admit how much we have yet to learn. The story of the Coma Cluster is still being written, and each new chapter promises to be more astonishing than